Hello everyone, welcome to Wallah. So I hope you guys are doing well. And this is the one shot series for the Gate 2023. And in this series, we will cover the different topics in one shot, right? So here I am covering the heat transfer subject, right? And this is the lecture number 1. And this lecture number 1, I will cover the steady state conduction heat transfer, right? So in this session, what are the topics that I will cover, right? So first, please take a brief of those topics, right? So we will start from the introduction part, right? We will start from the introduction part, then understand the steady state conduction heat transfer concept in Cartesian coordinate system, in the spherical coordinate system, and the spherical coordinate system, right? Because the problem that you are facing, the problem is based on the plane wall and the slab. So such type of problems are easy to deal with the Cartesian coordinate system, right? Then you are dealing with the problem based on the hollow cylinder or solid cylinder, right? So such type of problems are easily solved by the cylindrical coordinate system, right? And similarly, you are facing the problem based on the sphere, either it is a hollow sphere or it is a solid sphere, right? So such type of problems is easily solved by the spherical coordinate system. Getting my point, right? So first we will start from the introduction, right? Now, so in introduction part, if I ask you what is a heat transfer, right? First try to understand the basic concept. Now first try to understand the basic things, right? What is a heat transfer? So basically, heat transfer is the energy interaction or energy transfer between system and surrounding because of the temperature difference, right? There are different types of energy interaction between system and the surrounding, right? And if the energy interaction occurs due to the temperature difference, then that is known as the heat transfer. So basically, heat transfer, I say, heat transfer is an energy interaction. Heat transfer is an energy interaction or energy transfer. Energy interaction, energy interaction or energy transfer or energy transfer due to temperature difference. Due to temperature difference. Due to temperature difference. Okay. So let us assume there is a block. Let us assume there is a block having temperature 90 degrees Celsius. Let us assume. Okay. And let us assume that ambient temperature is, let us assume this is 30 degrees Celsius. 30 degrees Celsius. And if you drop this block in an environment or in an ambient, so definitely that heat transfer occurs. Definitely heat transfer occurs. So what is the direction of the heat transfer? What is the direction of the heat transfer? The direction of the heat transfer from high temperature body to low temperature body, because high temperature body having a high energy and the low temperature body having a low energy. So that heat transfer occurs from high temperature body to low temperature body. Is it fine? Right. So the direction of the heat transfer in this case is from the block to the ambient. Right. So if I ask you which law governs the heat transfer, or heat transfer is governed by which law? Heat transfer is governed by which law? Right. So in thermodynamics, we studied about the first law of thermodynamics. We studied about the 0th law of thermodynamics, first law of thermodynamics, second law of thermodynamics, and the third law of thermodynamics. So if I ask you heat transfer is governed by which law of thermodynamics, so what is your answer? What is your answer? So it is governed by the second law of thermodynamics. The heat transfer is governed by the second law of thermodynamics, because second law of thermodynamics right? Second law of thermodynamics is a directional law, right, which comment on a direction of a process, right? The first law of thermodynamics does not comment on the direction of the process. Second law of thermodynamics comment on the direction of the process, and as per the second law of thermodynamics, that flow of energy occurs from high energy to low energy naturally. And similarly, here the heat transfer is also the energy transfer, no? And energy transfer occurs due to the temperature difference. And since it occurs due to the temperature difference, so what is the direction? The direction is from high temperature body to low temperature body, because high temperature body having high energy and the low temperature body having low energy, right? So if anyone asks you which law of thermodynamics governs the heat transfer, so what is the answer? That answer is second law of thermodynamics. Answer is second law of thermodynamics. So second law of thermodynamics governs the direction of heat transfer, right? Or heat transfer governs by the second law of thermodynamics. Okay, now see, already in thermodynamics we studied about the heat transfer, right? But question is that why there is a need of a different subject? Please try to understand my question. Why there is need of a heat transfer subject? Because already we discussed about the heat transfer in the thermodynamics subject, but why there is need of a different subject? So this is the question which generally asked in the interviews, okay? Not in the gate exam or not any competitive exam, generally asked in the interviews, right? What is the difference between the thermodynamic subject and the heat transfer subject? Why heat transfer subject is a different subject, right? Now see, in thermodynamic subject, please try to understand, no? In thermodynamic subject, okay, fine, we already studied about the heat transfer. Now please try to understand this difference by this example, right? So let us assume I am considering a cup of tea. So this is the cup, and cup wall having thickness, let us assume this is delta. Okay, this is the cup, and cup wall having temperature delta. So this is the thickness, which is delta, right? And in cup there is a tea, okay. Now see, let us assume temperature of tea, let us assume this is 90 degrees Celsius. The temperature of tea is 90 degrees Celsius. Let us assume, na? Temperature of the tea is 90 degrees Celsius. And ambient temperature that is 30 degrees Celsius. Ambient temperature is 30 degrees Celsius. So if I ask you, what is the heat transfer from 90 degrees Celsius to 30 degrees Celsius? Because from the thermodynamics concept we know that after some time interval this T come into thermal equilibrium with the ambient. We know that. We know this concept. Thermal equilibrium concept, we know that from the thermodynamics point of view, right? So after some time interval the T come into thermal equilibrium with the ambient. So if I ask you what is the final temperature of the T, initial temperature of the T is 90 degrees Celsius. And what is the final temperature of the T? So final temperature of the T is 30 degrees Celsius. So if I ask you what is the total heat transfer from 90 degrees Celsius to 30 degrees Celsius, are you able to answer this question? Yes, sir, we are able to answer this question from the thermodynamics point of view, right? And or we can say whatever the concept we studied in the thermodynamics, from those concepts we are answer to this question, right? If I ask you what is the total heat transfer, so what is the total heat transfer? Now see, the total heat transfer, the total heat transfer, total heat transfer, that is equal to total heat transfer, that is equal to decrease in the internal energy of the T, है ना? Definitely that internal energy of the T decreases. So the total rate of heat transfer, if you simply apply the energy balance, the total heat transfer is equal to decrease in internal energy of the T. Decrease in internal energy decrease in internal energy of T. Okay, so Q, that is equal to decrease in internal energy. So how you will find the decrease in internal energy? It is simple na, m into c into delta T, mass of T into specific heat of the T into delta T, temperature difference. And what is the temperature difference? The temperature difference is 90 degrees Celsius to 30 degrees Celsius. The temperature difference is 90 degrees Celsius to, the temperature difference is 90 minus 30. Right, so m is the mass, C is the specific heat, and delta T is the temperature difference. So from the concept of thermodynamics, we are easily find out the total heat transfer, right? But now my question is that, what is the time required? What is the time required to reach the temperature from 90 degrees Celsius to 30 degrees Celsius? What is the time required? Are you able to answer this question? What is the time required to reach the temperature of the T from 90 degrees Celsius to 30 degrees Celsius? Are you able to answer this question? Right, what is the time? What is the time? Right, what is the time? What is the time? This is the question. So I think that answer is no. I think that answer is no. From the thermodynamics concept, we are not able to answer this question. What is the time required? Right. And similarly, there are some question also. Let us assume this is the first question. No, second question. The second question is that obviously that initial temperature is 90 degrees Celsius, and after some time the temperature is 30 degrees Celsius. After some time the temperature is 30 degrees Celsius. Right. So let us assume from 90 degrees Celsius to 30 degrees Celsius, the time required is 2 minutes. The time required is 2 minutes, or I can say 120 seconds. Time required is 2 minutes or 120 seconds. Now my question is that, okay, at time tau is equal to 0, the temperature of the T is 90 degrees Celsius. At time tau is equal to 120 seconds, the temperature of the T is 30 degrees Celsius. Now in between, let us assume if I ask you what is the temperature at time T is equal to 80 seconds. At time tau is equal to 80 seconds P, what is the temperature? What is the temperature of the T? Are you able to answer this question? No sir, we are not able to answer this question. Getting my point? Okay. Now see again. Now third question is from 90 degrees Celsius to 30 degrees Celsius, we know the total heat transfer now. We know the total heat transfer from the thermodynamic concept. What is the total heat transfer? Decrease in the internal energy. Okay, and that is calculated by m into c into delta T. Now 90 degrees Celsius to 30 degrees Celsius. If I ask you what is the heat transfer? What is the heat transfer at tau is equal to 80 seconds? At tau is equal to 80 seconds, because every second that heat transfer is not same, right? Every second the heat transfer is not same, right? At time tau is equal to 0, the heat transfer is different. At time tau is equal to 50 seconds, that rate the heat transfer is different, right? So if I ask you this question, at time tau is equal to 80 seconds, what is the heat transfer? You are not able to answer these questions, right? So this is the third question, right? What is the fourth question? What is the fourth question? The fourth question is that at time tau is equal to 0, the temperature is 90 degrees Celsius. 90 degrees Celsius. Right. Finally, it reaches to temperature 30 degrees Celsius. That is also fine. Right. Let us assume in between there is a temperature 60 degrees Celsius. In between, let us assume there is a temperature 60 degrees Celsius. So 90 degrees Celsius to 30 degrees Celsius. The 60 degrees Celsius definitely come. Right. So at what time the 60 degrees Celsius temperature reaches? At what time the 60 degrees Celsius temperature reaches? Right. So answer of this question we don't have from the thermodynamics concept. Right. Now see, next. So it is clear, it is very much clear, the temperature of the T changes with respect to time. Right. It is very much clear that temperature changes with respect to time. It is very much clear. Temperature changes with time. Okay. Now see, my question is, how the temperature changes with time? It changes linearly, or it changes exponentially, or it changes logarithmically, or it changes hyperbolically. How the temperature changes with respect to time? Are you able to answer this question? No, sir, we are not able to answer those questions. Getting my point? So there are number of examples, there are number of questions on those examples, right? Answer of such type of question we are not able to give the answer of such question from the thermodynamics concept. Right. Similarly, let us assume now focus on the wall of the cup. Now focus on the wall. In this portion. Focus on this wall. Right. So let us assume I draw that wall portion only, na? Wall portion only. So this is the wall. Let us assume this is the wall. This is the wall. Okay. And what is the thickness of the wall? The thickness of the wall is delta. Thickness of the wall is delta. This is the x direction. This is the x direction. This is the wall. Right, that cup wall having thickness delta. Thick, fine. Now see, let us assume this is the left face, this is the right face. Let us assume at time tau is equal to 0. At time tau is equal to 0. I am talking at time tau is equal to 0. At time tau is equal to 0, what is the temperature of the T? 90 degrees Celsius. Now I am assuming this wall also having temperature 90 degrees Celsius. Okay. This side T. Okay. T is present on this side and the ambient is present on this side. Ambient temperature is T infinity, which is 30 degrees Celsius, and T temperature is 90 degrees Celsius at time tau is equal to 0. So let us assume the left face of the wall also having temperature 90 degrees Celsius. I am neglecting the convection resistance right now. Right? What is the convection resistance? We will discuss those parts later on. But from very simple understanding, I'm assuming here the temperature is 90 degrees Celsius. Okay. So this wall having temperature 90 degrees Celsius, and similarly this wall having temperature 30 degrees Celsius. Okay. So definitely if I say at x is equal to 0, this is the x is equal to 0 now. X is equal to 0, the temperature is 90 degrees Celsius, and x is equal to delta, the temperature is 30 degrees Celsius. Right. So definitely in x direction at time tau is equal to 0. Please try to understand. Na? At time tau is equal to 0, that temperature is changing with respect to space. The temperature is changing with respect to x. Yes or no? Right. If I say here the temperature is 90, here the temperature is 30. So in between 90, 80, then 75, then 70, 60, 65 like that. Temperature is decreasing with respect to x. Na? Now my question is that if I ask you one question, what is the temperature? Let us assume this is the x is equal to delta. If I ask you the question at x is equal to delta by 3, at x is equal to delta by 3, what is the temperature here? At x is equal to delta by at x is equal to delta by 3, what is the temperature? Right? Or if I ask you how the temperatures varies with respect to x, right? How the temperature at particular time, at time tau is equal to 0, how the temperature changing with respect to x. Temperature is a function of x. It is very much clear. But question is that how the temperature changing with respect to x. Are you able to answer this question? Are you able to answer this question? Okay. So see, from 90 degrees Celsius to 30 degrees Celsius, it varies like that. It varies like that. It varies like that. Right? So there are number of, I can say there are number of ways. Okay, there are number of ways. Is it fine? Is it fine? Right? So temperature is a function of x. It is very much clear. But how the temperature changing with respect to x? Okay, we are not answer this question from the thermodynamics concept. Similarly, at time tau is equal to 0, at time tau is equal to 0, at x is equal to 0, at time tau is equal to 0, at time tau is equal to 0, at x is equal to 0, the temperature is 90 degrees Celsius. Right? And if I ask you at time tau is equal to 10 seconds, if I ask you at time tau is equal to 10 seconds, what is the temperature? What is the temperature at x is equal to 0? At x is equal to 0, what is the temperature? Right? Means here the temperature is changing with respect to the time. Temperature is changing with respect to the time. So how the temperature changing with respect to time? At a particular space, at a particular section, right? That temperature is changing with respect to time. Now my question is that how the temperature is changing with respect to time? Right? That means, please try to understand these things. From the thermodynamics concept, we are not able to answer such question, how the temperature changing with respect to space, with respect to time. Getting my point? From the thermodynamic concept, yes, it is very much clear that temperature is function of space and time. Space means, okay, here the x direction, we see already x direction, no? Right? So space, temperature is a function of space, temperature is a function of time. But how the temperature changing with respect to the space and time, answer of this question we don't have. Right? So there are certain questions. There are certain questions, or I can say there are number of questions. There are number of questions. Answer of those questions are not possible from the thermodynamics point of view or thermodynamics concept. Is it fine? And that's why there is a need of a different subject, right? And that is a heat transfer. So if I ask you what is the difference, between the heat transfer and the thermodynamic subject? So we can say in thermodynamics subject, we are mainly focused on the total heat transfer, right? From one equilibrium state to another equilibrium state, what is the total heat transfer? So in thermodynamic subject, we are only focused on the total heat transfer from one equilibrium state to another equilibrium state. But in heat transfer subject, we are focused on the rate of heat transfer. We are focused on the rate of heat transfer. Rate means with respect to time, right? Rate means with respect to time. So in case of the heat transfer subject, right? In case of the heat transfer subject, we are focused on the rate of heat transfer. And similarly, in thermodynamic subject, we are not bothering how the temperature is changing with respect to the space, with respect to the time, right? But in heat transfer subject, we are focusing how the temperature is changing with respect to the space and with respect to the time, right? So there are some differences. So these differences will not ask in the GATE exam, right? But definitely in interview such type of question will ask. Okay, now come to the next part of the introduction. Heat transfer. What is the heat transfer? We already studied heat transfer is a energy transfer due to the temperature difference, right? Heat transfer is governed by the second law of thermodynamics. Now, what are the mode of heat transfer? What are the mode of heat transfer? Mode of heat transfer. Mode of heat transfer. What are the mode of heat transfer? Right. So first mode of heat transfer, the first mode of heat transfer is conduction. That first mode of heat transfer is conduction. The first mode of heat transfer is conduction. Right. Second mode of heat transfer is convection. Second mode of heat transfer is convection. And third mode of heat transfer is radiation. Third mode of heat transfer is radiation. So there are three mode of heat transfer: conduction, convection and the radiation. So in introductory part, in introduction wala part mein, we will discuss about the different governing laws, right? If I say conduction heat transfer is governed by which law of conduction heat transfer is governed by which law, right? Or the convection heat transfer is governed by which law? See, the heat transfer is governed by the second law of thermodynamics. Heat transfer is governed by the second law of thermodynamics. But if I ask you, conduction heat transfer is governed by which law, then answer is different, na? Convection heat transfer is governed by which law? Answer is different. Radiation heat transfer is governed by which law? Right? So answer is different. Right? So in introduction wala part, in this introduction part, we will discuss about the governing laws. Right? If I ask you, conduction heat transfer is governed by, so there is a Fourier law of heat conduction. Convection heat transfer is governed by which law? That is the Newton's law of cooling. And if I ask you what is the radiation, what is the law that governs the radiation heat transfer? That is the Stefan-Boltzmann law, right? So conduction heat transfer. Conduction heat transfer. So what is the conduction? Right. So conduction is basically, if I ask you what is the conduction heat transfer, so basically the conduction heat transfer is a heat transfer that occurs in a solid, or that occurs in two different medium which are in direct physical contact, right? The conduction heat transfer is a energy transfer, or I can say conduction heat transfer is a heat transfer that occurs in a solid, and in solid from high temperature zone to low temperature zone, from high temperature zone to low temperature zone, or I can say the conduction heat transfer occurs in a two different medium which are in direct physical contact, right? So in this is a particular crash course now, this is a crash course, this is a one short crash course actually, right? So here I am dealing with the concept which are important in exam, right? So conduction heat transfer is governed by which law of conduction heat transfer is governed by which law? So conduction heat transfer is governed by Fourier law, of heat conduction, governed by Fourier law of heat conduction. Fourier law of heat conduction. Conduction heat transfer is governed by the Fourier law of heat conduction. Convection heat transfer, that convection heat transfer is governed by Newton's law of cooling. Right? That convection heat transfer is governed by the Newton's law of cooling, and the radiation heat transfer is governed by the Stefan-Boltzmann law. Right? So conduction heat transfer is governed by the Fourier law of heat conduction. Convection heat transfer is governed by the Newton's law of cooling, and the radiation heat transfer is governed by the Stefan-Boltzmann law. Right? Now come to the Fourier law of heat conduction. 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 Right. So if anyone asks you the conduction heat transfer is governed by which law, the answer is very simple. The conduction heat transfer is governed by the Fourier law of heat conduction. Right. So as per Fourier law of heat conduction, as per okay, so to understand the Fourier law of heat conduction or Fourier law of conduction heat transfer, I am considering a plane wall. I am considering a plane wall. I am considering a plane wall. Okay. And let us assume this plane wall having thickness dx. This plane wall having thickness dx, and that this is the left face, this is the right face, and the temperature difference across the wall is dt. So let us assume here the temperature is T plus dt, and here the temperature is T. Okay. Now the cross sectional area is A. Right, the cross sectional area is A. So left phase having temperature T plus dt, right phase having temperature T. So temperature difference across the wall occurs, and because of this, that heat transfer within this wall occurs. Okay, right. Here the temperature is T plus dt, here the temperature is T. Temperature difference is there, temperature gradient exists, and because of that heat transfer occurs. So within this wall or within this slab, that mode of heat transfer is conduction. The mode of heat transfer is conduction. Okay, so as per the Fourier law of conduction, as per Fourier law of conduction, this rate of conduction heat transfer, what is the q dot? First define what is the q dot. The q dot is rate of conduction heat transfer. Right. And this rate of conduction heat transfer is directly proportional to the temperature difference. Right. Left phase and right phase, what is the temperature difference? That is dt. And this rate of conduction heat transfer is directly proportional to the temperature difference. Right. If dt is more, then definitely the rate of conduction heat transfer will be more. Okay. Now similarly, this rate of conduction heat transfer is directly proportional to area A. And what is this area? This area is normal to the direction of conduction heat transfer. What is the area A? Okay, this area A is please na, very important. This area A is normal to direction of conduction heat transfer. Right. A is the area which is normal to the direction of the conduction heat transfer. Right. Now see next, and this is the practical observation. These are the practical observation which were made by the Fourier. Right. These are the practical observation which were made by the Fourier a long time back. Is it fine? Fourier law of heat conduction is not derived from any first principle. It is not derived from any first principle. It is the practical observation which was made by the Fourier. Right. Similarly, this rate of conduction heat transfer, this rate of conduction heat transfer is directly proportional to 1 by dx, or I can say it is inversely proportional to the thickness. It is inversely proportional to the thickness. What is dx? The dx is thickness, right? So if we are combine all this, so we can write the rate of conduction heat transfer is directly proportional to this is the A dt by dx. Yes or no? Right. Rate of conduction heat transfer is directly proportional to A dt by dx. And what is the dt by dx? The dt is the temperature difference, dx is the thickness. What is the dt by dx? The dt by dx is temperature gradient. Temperature gradient in x direction. Temperature gradient in x direction, right? So what is the dt by dx? The dt by dx is the temperature gradient in x direction, right? Now see here that Q rate of conduction heat transfer is directly proportional to A dt by dx, right? So there is a proportionality sign is there, and if you remove the proportionality sign, then that constant come into picture, है ना? If you remove the proportionality sign, then constant come into picture. Okay, now see, rate of conduction heat transfer is equal to, if you remove the proportionality sign, then proportionality constant come into picture, and this proportionality constant, let us assume this is C A dt by dx. Okay, now this C, this constant, this proportionality constant is very, very important. This proportionality constant is very, very important. Why this proportionality constant is important? Because this proportionality constant depends on the material, right? This proportionality constant depends on the material, and here we consider a wall. So definitely, what is the wall material, right? C is the proportionality constant which depends on the material, right? So material of wall is made of steel, or wall is made of the copper, or wall is made of the aluminium. What is the material of the wall? So this proportionality constant depends on the material of the wall, and that's why we can say this constant, this proportionality constant is a material property. This is a material property. This proportionality constant is a material property, and this material property is known as thermal conductivity. And it is denoted by small k, not capital K, small k. Capital K is for Kelvin, small k. So this proportionality constant is a material property, depends on the material, right? And this proportionality constant is known as the thermal conductivity, and it is noted by K, right? So we can write this mathematical expression like this: the rate of conduction heat transfer, this is Ka dt by dx. Now please try to understand now. In the direction of heat transfer, the temperature decreases now. See, this is the x direction now. This is the x direction. This is the x direction. In x direction, the conduction heat transfer occurs. In x direction, conduction heat transfer occurs, and it is very much clear. In a x direction, the temperature decreases. As x increases, the temperature decreases. As x increases, temperature decreases. Therefore, the dt by dx is negative now. The dt by dx is negative. Yes or no? Yes or no? X increases, So dx is positive, temperature decreases, so dt is negative. So negative by positive, that is negative, right? So dt by dx, the temperature gradient in the direction of conduction heat transfer decreases, right? So so to make the to make this rate of conduction heat transfer positive, see, in this term, in this mathematical expression, thermal conductivity is not negative, right? A is not negative. The dt by dx is negative. dt by dx is negative, right? So to make the rate of conduction heat transfer positive, to make the conduction heat transfer or rate of conduction heat transfer positive, I am putting a minus sign here. I am putting a minus sign here because dt by dx is negative, right? This is negative, so negative, negative, positive. So why this minus sign is there? Why this minus sign is here? Minus sign is here to make the rate of conduction heat transfer positive, right? Or we can say another way also, minus sign shows in the direction of conduction heat transfer. Minus sign shows in the direction of conduction heat transfer, temperature decreases. Is it fine? Is it clear? Is it clear? Minus sign shows, minus sign shows in the direction of, in the direction of conduction heat transfer, in the direction of conduction heat transfer, temperature decreases, temperature decreases. Fine. Chaliye. Now see, now the rate of conduction heat transfer, is equal to minus k a dt by dx, minus k a dt by dx. And what is the unit of, now see, what is the unit of rate of conduction heat transfer? What is the unit? Rate of conduction heat transfer. So basically this is the rate of energy transfer now. This is the rate of energy transfer. And what is the unit of the energy? Joule. What is the unit of the time? Second. So joule per second, and joule per second is a watt. So rate of conduction heat transfer, what is the unit? That unit is watt. Fine. Now see, can I write in this way also? The rate of conduction heat transfer by A, right? The rate of conduction heat transfer per unit area. The rate of conduction heat transfer per unit area, or rate of heat transfer per unit area, not only the conduction heat transfer, rate of heat transfer per unit area, that is known as the flux. And here heat flux or conduction heat flux, right? Conduction heat flux, q dot, small q dot. This is a conduction heat flux, conduction heat flux, and this is equal to minus k dt by dx, minus k dt by dx, minus k dt by dx, right? So Fourier law of heat conduction, Fourier law of heat conduction, Fourier law of heat conduction, Fourier law of heat conduction. This is the Fourier law of heat conduction. You can write in this way also. You can write in this way also. Fine. Now see, what is the unit? What is the unit? Unit of K. What is the unit of K? What is the unit of K? What is the unit of K? Unit. What is the unit of K? Right. So unit, that K is equal to, we can write in this way, this is the rate of conduction heat transfer by A dt by dx. Okay. So what is the unit? Now rate of conduction heat transfer, that is what? Watt. What is the area? This is the meter square. What is the dt? Dt, na? Dt is the temperature difference. Either you take in degree Celsius or in Kelvin, the meaning will be same. The temperature difference, na? Temperature difference. So temperature difference, Kelvin. And what is the dx? So this is the distance and this is meter. So Okay, so what is the unit ultimately? This comes watt per meter Kelvin. Watt per meter Kelvin, or we can say watt per meter degree Celsius also, na? Watt per meter degree Celsius. If let us assume some material having thermal conductivity is given 12 watt per meter degree Celsius. Now most of the students are panic here because that unit is given in watt per meter degree Celsius, and there is a need of watt per meter Kelvin, right? So there is no need to be panic. 12 watt per meter degree Celsius is equal to 12 watt per meter Kelvin only, because degree Celsius is there for temperature difference, and temperature difference, either you take the temperature difference in Kelvin scale or you take the temperature difference in degree Celsius scale, meaning will be same. Okay, so this is the unit of thermal conductivity. This is the unit of the thermal conductivity. Thermal conductivity. Now, this Fourier law of heat conduction has na certain assumptions. This Fourier law of heat conduction has a certain assumptions, like material is a homogeneous and the isotropic, right? That wall material is homogeneous and the isotropic, right? That thermal conductivity K is constant. Thermal conductivity K is constant, one dimensional, steady state, right? So I can say there are number of assumptions for the Fourier law of heat conduction, right? And that is why if these assumptions are not valid, right? Fourier law of heat conductions are valid under certain assumptions. What are those assumptions? Material is homogeneous, isotropic, no internal heat generation within the wall, right? And thermal conductivity is constant, steady state condition is maintained, right? So there are a number of assumptions. So Fourier law of heat conduction is valid under certain assumptions. But if these assumptions are not valid, then 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 there is a general heat conduction equations, right? General heat conduction equations, please try to understand now. If Fourier, why there is need of a general heat conduction equation? Why there is a need of general heat conduction equation? Such type of question is asked in the interview also. We have the Fourier law of heat conduction. We have the Fourier law of heat conduction, but why there is a need of a general heat conduction equation? So answer is that the Fourier law of heat conduction has a certain assumptions, right? And if these assumptions are not valid, then there is a need of another equation, right? And that another equation is nothing but the general heat conduction equation. And that's why we will study the general heat conduction equation in the Cartesian coordinate system, in the cylindrical coordinate system, and in the spherical coordinate system. Okay, fine. Okay, now, so this is introduction. This is introduction part of Fourier law of heat conduction. Now come to the Newton's law of cooling. Now come to the Newton's law of cooling. Newton's law of cooling. Newton's law of cooling. Newton's law of cooling. Right. Now, that convection is basically made of two terms. Convection is basically made of two terms. One is a conduction and another one is a advection. Right. Convection, if I'm talking about the convection, this convection word is made of two another words. One is conduction plus advection. Conduction plus advection. Okay, and what is the advection? That advection means motion of fluid particles. Motion of fluid particles, right? And this motion is either created naturally or it is created by the some external agent, right? This motion is either created naturally. Okay, the motion of what? Motion of the fluid particles, right? Motion of the fluid particles. So this motion is either created freely, or I can say naturally, freely or naturally, or it will create forcefully, forcefully, right? So if the motion, if the motion of the fluid particle, if the motion of the fluid particle is created naturally or freely, then it is called natural convection. Then it is called natural convection, or free convection, natural convection or free convection. But if the motion is created forcefully, then it is called forced convection, forced convection, right? And in between there is a mixed convection also, right? So either you are talking about the free convection, or you are talking about the forced convection or mixed convection. Whatever the type of convection, the convection heat transfer is governed by the Newton's law of cooling, right? Whatever the type of convection, either it is a free, either it is a force, or it is a mixed convection, any type of convection heat transfer is governed by the Newton's law of cooling, right? Now see, Newton's law of cooling. So to understand the Newton's law of cooling, okay. Now see, what is a free convection, what is a forced convection? We will discuss this part in a convection heat transfer topic, right? How that free motion created, how the motion created freely, or how the motion created forcefully, right? This part we will cover in the convection topic, right? Here I am just telling very introduction part, right? Newton's law of cooling. So Newton's law of cooling by the convection heat transfer is governed by which law? So convection heat transfer is governed by the Newton's law of cooling, right? So to understand the Newton's law of cooling, I'm considering a plate here. To understand the Newton's law of cooling, I'm considering a plate, and let us assume plate having temperature that is T infinite. Sorry, a plate having temperature TW. And this is the fluid which is flowing over the plate. And let us assume this fluid having temperature T infinity and temperature is U infinity. And free stream temperature is T infinity. And the free stream velocity is U infinity. And let us assume TW is greater than the T infinity. Okay. This is the x direction. This is the y direction. This is the y direction. Okay. Now at y is equal to 0, we know from the fluid mechanics concept, at y is equal to 0, right? No relative velocity exists between the plate and the fluid. At y is equal to 0, no relative velocity exists between the plate and the fluid particle. What is the meaning of that? Whatever the velocity of the plate have, same velocity of the fluid particle also there. At y is equal to 0. Whatever the velocity of the plate have, the same velocity of the fluid particle also have at y is equal to 0, at y is equal to 0. Right. So let us assume a plate is stationary. If I am assuming the plate is stationary, so at y is equal to 0, at y is equal to 0, at y is equal to 0, that velocity of the fluid particle is also 0. Because at y is equal to 0, again I am telling you guys, at y is equal to 0, at y is equal to 0, what is the velocity of the fluid particle? The velocity of the fluid particle is same as velocity of the plate. So if the plate is stationary, if the plate is stationary, if the plate is stationary, I am assuming here this plate is stationary. I am assuming here this plate is stationary. So if plate is stationary, that UP is equal to 0. Plate velocity is 0, and that's why the velocity of the fluid particle at y is equal to 0, that is also 0. This is called no slip condition. 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 Right? Because no slip condition, slipping occurs when relative velocity exists. If there is no relative velocity, there is no slipping. That's why this condition is known as the no slipping condition. Right? Now see, at y is equal to 0, fluid and the solid are direct in physical contact. So what is the mode of heat transfer? Please try to understand. In conduction, I told you the conduction heat transfer occurs within the solid from high temperature zone to low temperature zone. Or in conduction heat transfer, conduction heat transfer occurs within the solid from high temperature zone to low temperature zone, or two different medium which are in direct physical contact. Right? The conduction heat transfer occurs in a solid from high temperature zone to low temperature zone, or two different medium which are in direct physical contact. And here at y is equal to 0, at y is equal to 0, now see, at y is equal to 0, what happened? See, this is the fluid particle. This is the fluid particle at y is equal to 0. And this is the plate particle. This is the plate particle at y is equal to 0. So at y is equal to 0, at y is equal to 0, solid, that means plate particle, and the fluid particle both are in direct physical contact. Right? And TW is the temperature of the plate, TW is the temperature of the plate, and T infinity is the temperature of the fluid. So definitely the heat transfer occurs now. See, the heat transfer occurs like this, from plate to the fluid, from plate to the fluid. Yes or no? From plate to the fluid. Yes or no? Okay, so what is the mode of heat transfer? At y is equal to 0, what is the mode of heat transfer? So my dear, at y is equal to 0, that mode of heat transfer is a conduction. At y is equal to 0, that mode of heat transfer is a conduction. Right? Please try to understand now. Convection is made of two terms, conduction plus advection. Conduction plus advection. Advection means motion. If there is no motion, if let us assume there is no motion is there. Getting my point? So if there is no motion, then conduction is equal to convection. If there is no conduction, let us assume the plate temperature and the fluid temperature is same. Let us assume plate temperature and the fluid temperature is same. Any heat transfer occurs? No. There is no heat transfer. Getting my point? So convection is not there. Na? Convection is equal to advection. There is only motion. There is no heat transfer. So please try to understand this logic. Convection is made of two terms, conduction plus advection. If there is a conduction, then there is a convection. If there is no conduction, there is no convection. There is only motion. Is it fine? So at y is equal to 0, that mode of heat transfer is conduction. And if there is a motion, then we can say, not only we can say conduction, we can say conduction plus motion. So we can say this is the convection. Getting my point? So here the motion is there, right? The fluid particle is moving with certain velocity, right? So motion is created, or motion will create either freely or forcefully. Forcefully means some with the help of some external agent. Naturally means with the help of the temperature difference, that density difference occurs, and because of some buoyant force, that hotter particles moving upward and the colder particles moving downward, right? That we will see in the convection topic. Okay, now see. So so Newton's law of cooling. So there is a plate having temperature Tw, fluid having temperature T infinitive, right? So as per Newton's law of cooling, 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 the rate of convection heat transfer, as per Newton's law of cooling, the rate of convection heat transfer, that is equal to, or I can say the rate of convection heat transfer is directly proportional to Tw minus T infinitive, है ना? The rate of convection heat transfer is directly proportional to Tw minus T infinitive. What is the Tw? Plate temperature. What is the T infinitive? Free stream temperature of the fluid, right? Rate of convection heat transfer is directly proportional to the area. Which area? Area from where that convection heat transfer occurs, or area which is responsible for the convection heat transfer, right? So if you combine both the things, then we can say the rate of convection heat transfer is directly proportional to A Tw minus T infinitive. A Tw minus T infinitive, right? Now again, if I remove the proportionality sign, then proportionality constant come into picture, then proportionality constant come into picture, right? And that proportionality constant is H. That proportionality constant is H, or you can say the proportionality constant is C. Then ultimately C can we write H, right? C we can write H. So I can directly say that proportionality constant is H. Proportionality constant is H. And what is the H? What is the H? This H is convective heat transfer coefficient. This H is convective heat transfer coefficient. This H is convective heat transfer coefficient. But this H is not like a thermal conductivity. That convective heat transfer coefficient, or simply heat transfer coefficient, this convective heat transfer coefficient is not like a thermal conductivity. Thermal conductivity depends on the material. But this convective heat transfer coefficient depends on the number of things. Okay? That convective heat transfer coefficient H, depends on A. Depends on that convection is free convection or forced convection, right? Same plate, same fluid, but the convection heat transfer is free convection or forced convection. So that H value is different for the free convection, H value is different for the forced convection. So that value of H depends on the free convection or forced convection. Free convection or forced convection, right? Second, the H depends on the type of the fluid. What is the meaning of that? Type of the fluid means type of the Fluid means gas is flowing over the plate or liquid is flowing over the plate. Gas or liquid. Gas or liquid. Right. H depends on the type of flow. Type of flow. What is the meaning of that? Over the plate, flow is laminar or turbulent. Over the plate, flow is laminar or turbulent. Right. Next, D. Next, surface finish of the plate. 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 That means plate is rough, rough or mirror polished. Rough or mirror polished. Mirror polished, right? Surface finish of the plate. Next, orientation of the plate. Orientation of the plate. Orientation of the plate. What is the meaning of that? Plate is horizontal or plate is vertical or plate is inclined. Right? Plate is horizontal or plate is vertical or plate is inclined. Plate is horizontal or vertical or inclined. Right? So that H value depends on the number of things. Free convection or forced convection, type of the fluid, type of the flow, surface finish, orientation of the plate. Right? So it is not like a thermal conductivity. The thermal conductivity only depends on the type of the material, but H depends on the number of things. Right? Now what is the unit of H? What is the unit of H? Now the rate of convection heat transfer is equal to, this is H into A into TW minus T infinity, right? So H is equal to rate of convection heat transfer A TW minus T infinity, right? So H unit, what is the unit of rate of convection heat transfer? So that is watt meter square, and TW minus T infinity, temperature difference, no? So either you can write in Kelvin or you can write in degree Celsius. So watt per meter Kelvin, or you can write watt per meter degree Celsius. Right? This is the unit of the H. Now, are you able to write H in terms of the fundamental dimensions? Fundamental dimensions, right? Are you able to write the H in terms of the fundamental dimensions? Fundamental dimensions. So how many fundamental dimensions are there? How many number of fundamental dimensions? So total there are 7 fundamental dimensions, and heat transfer we are using the 4 fundamental dimensions. Right? Out of the 7 we are using the 4. So mass m, length L, time T, temperature theta. Right? Mass m, length L, time T, temperature theta. Right? Now see here, H, write the H in terms of the fundamental dimension. So watt per meter square Kelvin. So watt joule per second, and joule per second, that means Newton meter per second, na? Newton meter per second, meter square Kelvin, meter gone, right? And no, Newton. So Newton is mlt minus 2. Newton, unit of force, mlt minus 2. Second, T, meter, L, temperature theta. So L L over, so M T minus 3, T minus 3, theta minus 1, M T minus 3, theta minus 1. Okay, so this is H in terms of the fundamental dimensions. H in terms of the fundamental dimensions. And are you able to write the K thermal conductivity in terms of the fundamental dimensions? I think earlier we forget. But are you able to write thermal conductivity in terms of fundamental dimensions? K in terms of fundamental dimensions. Yes, sir. Now K in terms of fundamental dimensions. So K, that is watt per meter Kelvin. Now watt per meter Kelvin. So watt per meter Kelvin, again this is Newton meter second, and this is meter and Kelvin. So meter over. Now Newton M L T minus 2 and second T K theta. So ultimately this is M L T minus 3 theta minus 1. This is the K in terms of fundamental dimensions. In terms of fundamental dimensions. In terms of fundamental dimensions. ठीक है, M L T minus 3 theta minus 1. Fine. Okay, now Newton's law of cooling is over. Now come to the next. Okay, and one thing also, that convective heat flux. So convective heat flux, that Q dot convection. This is the convective heat flux, and simply this is rate of convection heat transfer. Rate of convection heat transfer per unit area. So this is H TW minus T infinitive. H TW minus T infinitive. Okay, this is the convective heat flux. Fine. Now come to the next law, and that is the Stefan-Boltzmann law. Next law is the Stefan-Boltzmann law. The radiation heat transfer is governed by Stefan-Boltzmann law. Stefan-Boltzmann law. Stefan-Boltzmann law. Right. So convection heat transfer, radiation heat transfer is governed by the Stefan-Boltzmann law. So what is the Stefan-Boltzmann law? What is the Stefan-Boltzmann law? So let us assume, to understand the Stefan-Boltzmann law, I am considering a black body. This is the black body. This is the black body. And let us assume this black body having temperature T. This black body having temperature T. This is a black body, and the black body having temperature T. Okay. Now, please try to understand. If I'm talking about the radiation heat transfer, so any body having temperature above 0 Kelvin temperature, or I can say any body having temperature above the absolute temperature, right, above the absolute 0 temperature, that always emits the radiation energy. So any body having temperature above 0 Kelvin temperature always emits the radiation energy, and that radiation energy is in the form of you can say electromagnetic wave, or you can say in the form of the photons. So basically in radiation heat transfer, two types of theories are used. One is the Maxwell's electromagnetic wave theory, and second one is the Planck's photon theory. So basically we engineers prefer the Maxwell electromagnetic wave theory, right? So radiation, we assume that the radiation is in the form of the electromagnetic wave, right? We engineers assume that radiation is in the form of the electromagnetic wave, because we are preferring or we are using the Maxwell's electromagnetic wave theory to understand the radiation heat transfer. Fine. Now I am considering a black body. That black body having temperature T, which is above the 0 Kelvin temperature, and any body having temperature above 0 Kelvin temperature that emits the radiation energy. That emits the radiation energy in the form of the electromagnetic wave, right? So this black body also emits the radiation energy. This black body also emits the radiation energy. This black body also emits the radiation energy. Radiation energy. Right? And as per the Stefan-Boltzmann law, as per the Stefan-Boltzmann law, as per the Stefan-Boltzmann law, as per Stefan-Boltzmann law, Stefan-Boltzmann law, radiation energy, or I can say total radiation energy, na? That total radiation energy, total radiation energy, total radiation energy emitted by a black body, per unit time, per unit time, per unit time, per unit area, per unit time, per unit area is directly proportional to, is directly proportional to, is directly proportional to fourth power, is directly proportional to fourth power of absolute temperature, fourth power of absolute temperature, fourth power of absolute temperature, right? As per the Stefan-Boltzmann law, that total radiation energy emitted by a black body per unit time, per unit area is directly proportional to the fourth power of the absolute temperature. Absolute temperature means temperature is in Kelvin scale, है ना? Temperature is in Kelvin scale. ठीक? Now question is that what is the black body? Basically black body is a body which is perfect absorber. Perfect absorber. Apart from that there are different property also there, right? But at the initial phase, at least you understand the black body is a body which is a perfect absorber. Whatever the radiation energy is strike to that body, that body absorb all the radiation energy. That is known as the black body. Apart from that, the black body is a perfect emitter as well as the perfect absorber. Okay. Those are another properties that we will see in the radiation topic itself, right? But filhal, right now, at least you understand what is the black body. So black body is a body which is perfect absorber. So whatever the radiation energy falling on that body absorb all the radiation. Fine. Now see, so Stefan-Boltzmann law says the radiation energy, the total radiation energy emitted by a black body per unit time, per unit area, per unit time, per unit area is directly proportional to absolute temperature to the power 4, right? And this radiation energy, this total radiation energy, here I am talking about the total radiation energy, and this total radiation energy is also known as the emissive power. This total radiation energy is also known as the emissive power. So if I say emissive power, so what is the emissive power? Emissive power, emissive power, emissive power, emissive power, and it is noted by E. And here we are talking about the black body, so this is EB, this is EB, right? So emissive power, that is EB. And what is the emissive power? So emissive power is the total radiation energy emitted, total radiation energy emitted by a body per unit time per unit area, right? Here I am talking about the black body, so I can say emissive power of a black body, right? So emissive power is denoted by E. Since here we are talking about the black body, that's why I say this is EB. So this EB, this EB, this EB, this is the emissive power of a black body. This is directly proportional to T to the power 4. This is directly proportional to T to the power 4. Is it fine? Is it fine? Okay. Now what is the unit? What is the unit of the EB? So definitely that is watt per meter square, correct? Now proportionality sign. Remove the proportionality sign. If you remove the proportionality sign, then proportionality constant come into picture, and that proportionality constant is sigma B T to the power 4. And what is sigma B? What is the sigma B? That is known as the Stefan-Boltzmann constant. Stefan-Boltzmann constant. Stefan-Boltzmann constant, right? And the sigma B is equal to, this is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Watt per meter square Kelvin to the power 4. Right. So that EB is equal to sigma B T to the power 4. So what is the unit? That is watt per meter square. Watt per meter square, na? Watt per meter square. That's sigma B. Watt per meter square Kelvin to the power 4. T Kelvin to the power 4. So Kelvin to the power 4, Kelvin to the power 4 cancel out. So what is the unit? That unit is watt per meter square. Watt per meter square. Right. So EB, that is the emissive power of a black body, right? And if I want to write in watt, so that EB is equal to, this is sigma B A. And what is the A? That A is the area of, A is the surface area of this black body, right? Temperature is T and A is the area. So sigma B A T to the power 4. T to the power 4. And that is watt per meter. Sorry, watt in watt. That is okay. So this is about the emissive power. This is about the total radiation energy emitted by a black body. But if I ask you, there are two black bodies, and both the black bodies are at different temperature. Both the black bodies are at a different temperature. Let us assume there is a one black body. Let us assume there is a one black body, and let us assume there is a another black body. Right? Both are black bodies. This is the black body having temperature T1. This is the black body having temperature T2. Right? Let us assume area is A1 and here area is A2. Right? And T1, let us assume T1 is greater than T2 here. I am assuming T1 is greater than T2. T1 is greater than T2. Right. So definitely the radiation heat exchange occurs between these two black bodies. For the heat transfer, what is required? What is the driving potential? For the heat transfer, either talking about the conduction or talking about the convection or talking about the radiation. What is the driving potential for the heat transfer? The driving potential is the temperature difference, right? And here two black bodies, and both the black bodies having a different temperature, T1 and T2. T1 is greater than T2. So definitely that heat exchange occurs. Definitely that heat exchange occurs between these two bodies. So if I ask you, what is the net radiation heat exchange? What is the net radiation heat exchange between these two black bodies? What is the net radiation heat exchange between these two black bodies? Is it fine? Is it fine? Is it fine? What is the net radiation heat exchange between these two black bodies? So what is the net radiation heat exchange? So I simply write that net radiation heat exchange, between body 1 and 2 or black body 1 and 2, this is A1 F12 sigma b T1 to the power 4 minus T to the power 4. And how this mathematical expression come? How this mathematical expression come? That we will discuss in the radiation topic, radiation heat transfer topic. Right. Right now, you directly remember what is the net radiation heat exchange between these two black bodies. So that net radiation heat exchange between these two black bodies is this. The net radiation heat exchange between these two black bodies is A1 F12 sigma b T1 to the power 4 minus T to the power 4. And what is the F12? This is very very important. F12, right? That F12 is known as the shape factor. Shape factor, or you can say view factor also. View factor. This F12 is a shape factor or view factor. Why this shape factor come? Why this shape factor come? See, please try to understand. Whatever the radiation energy, see, whatever the radiation energy emitted by the black body, all the radiation energy not striking to the black body number 2. Whatever the radiation energy emitted by a body number 1, whatever the radiation energy emitted by the black body number 1, all the radiation energy not striking to the black body number 2. The some part of the energy emitted by the body number 1, that strike to the body number 2. Getting my point? So to incorporate that part, view factor concept, or I can say shape factor concept, come into picture. So what is the shape factor? Basically, if I want to write F12, see, what is the F12? Now see, F12. So this is Q12 by Q. Q12 by Q1. What is the Q1? See, this Q1, please try to understand. What is the Q1? The Q1 is total radiation energy emitted by the body number 1. Total radiation energy emitted by the body number 1, let us assume this is 100. Right? But all the radiation energy emitted by the body number 1, that strike to the body number 2? No, because see, in this direction also the radiation energy emit, na? So this radiation energy not strike to this body, na? Right? So only the sum part of the 100 that strike to the body number 2, na? So let us assume Q12. What is the Q12? What is the Q12? The radiation energy which is emitted from the body number 1. Radiation energy which is emitted from the body number 1, and that strike to the body number 2. 1. See, radiation energy emitted by the body number 1. 2. Radiation energy strike to the body number 2. So what is the Q12? The Q12 is radiation energy emitted by the body number 1, and that radiation energy, see, Q12, radiation energy emitted by the body number 1, right? That strike to the body number 2. Q12, radiation energy emitted by the body number 1, that strike to the body number 2. That is the Q12. What is the Q1? Q1 is the total radiation energy emitted by the body number 1. What is the total radiation energy emitted by the body number 1? That is 100 unit, let us assume. So what is the Q12? The Q12 is, let us assume 50. It may be 40 also, 60 also. So let us assume I am considering 50. So what is the F12? So F12 is simply, I say, this is 50 divided by 100. Right, 1 by 2. Right, so this F12 is shape factor or view factor. So shape factor, view factor, that is very, very important concept. Number of times that question come from this shape factor and the view factor. This logic, this part we will cover in the radiation part. Okay, so right now we are discussing about the radiation heat exchange between two black bodies. If both the black bodies are at the same temperature, let us assume T1 is equal to T2. Let us assume T1 is equal to T2. There is no radiation heat exchange. There is no radiation heat exchange because T1 and T2 are same. If T1 and T2 are different, then there is a net radiation heat exchange. Right. So this is about the radiation heat exchange between the two black bodies. Right. Similarly, we will discuss about the radiation heat exchange between non-black bodies. This is all about the black bodies. This non-black bodies also, है ना? So radiation heat exchange between non-black bodies, that we will cover in the radiation term. Right. So here we will discuss only the introduction part. हम लोगों ने सिर्फ introduction part discuss किया. Right. Introduction part. Conduction heat transfer is governed by which law? Convection heat transfer is governed by which law? And the radiation heat transfer is governed by which law? Right. So conduction heat transfer is governed by the Fourier law of heat conduction. Convection heat transfer is governed by the Newton's law of cooling, and the radiation heat transfer is governed by the Stefan-Boltzmann. Okay, now let's start our discussion on conduction heat transfer. Right. So conduction heat transfer is divided into two parts. Right. One is the steady state conduction and another one is the unsteady state conduction. Right. Conduction heat transfer, conduction heat transfer. Conduction heat transfer is divided into two parts. Right. That first one is steady state conduction. Steady state conduction, and another one is unsteady state conduction. Unsteady state or transient, right? Unsteady state or transient unsteady state or transient conduction. Right. Or we can say steady state conduction heat transfer and the unsteady state conduction heat transfer. Right. In steady state conduction heat transfer, that temperature is only function of space. Temperature is only function of space. Right. Whereas in case of the unsteady state conduction heat transfer, temperature is function of space and time, or temperature is only function of time. Temperature is only function of time. Right. Now, either we are dealing with the steady state conduction heat transfer or we are dealing with the unsteady state conduction heat transfer. There is need of general heat conduction equation. There is need of general heat conduction equation. Right. General heat conduction equation. Now, might be you are thinking, sir, already we have the Fourier law of heat conduction. Why there is need of a general heat conduction equation? Why there is need of general heat conduction equation? So, I already told you that Fourier law of heat conduction has a certain limitations. Right. The Fourier law of heat conduction has certain limitation, and what are those limitations? Right. I already discussed the assumptions. Remember that assumptions? Right. Material is homogeneous and the isotropic. Right. There is no internal heat generation within the wall. Right. Thermal conductivity is constant, steady state. Right. So there are number of assumptions. Let us assume if these assumptions are not valid, then, right, let us assume in a problem internal heat generation occurs. Let us assume that thermal conductivity is not constant. Let us assume. Then in that case, how you are dealing with the problem? That's why there is need of a general heat conduction equation. Right. So Fourier law of heat conduction has a certain limitations, and this is the reason we need a general heat conduction equation. General heat conduction equation. Right. So we need general heat conduction equation in Cartesian coordinate. Right. Because there is a problem based on the plane wall and the slab. Such type of problem are easily solved by the Cartesian coordinate system. Right. there are number of problems which are based on the cylinder, hollow cylinder, or you can say solid cylinder, right? There are problem based on the hollow sphere or solid sphere, right? That's why we need a general heat conduction equation in Cartesian coordinate system, in cylindrical coordinate system, as well as in spherical coordinate system. So first here we will discuss about the general heat conduction equation in the Cartesian coordinate system, right? So general heat conduction equation in Cartesian coordinate system, in Cartesian coordinate system, in Cartesian coordinate system, right? To solve the problem, to solve the problem, which type of problem? To solve the plane wall slab related problem. To solve the plane wall slab related problem. Second, in cylindrical coordinate system, in cylindrical coordinate system, in cylindrical coordinate system, cylindrical coordinate system, to solve the problem based on the hollow cylinder, solid cylinder, solid cylinder, tube, pipe, etc. Okay. Similarly, in spherical coordinate system, in spherical coordinate system, in spherical coordinate system, to solve the problem based on the hollow sphere, solid sphere, to solve the problem based on the hollow sphere, solid sphere, etc. Right. So there is need of general heat conduction equation. Why there is need of general heat conduction equation? Because Fourier law of heat conduction has certain limitation, right? So overcome those limitations, there is need of the general heat conduction equation. Okay. Now come to the general heat conduction equation in the Cartesian coordinate. So next heading is general heat conduction equation, general heat conduction equation, general heat conduction equation in Cartesian, coordinate system, in Cartesian coordinate system. So in Cartesian coordinate system, in Cartesian coordinate system, that temperature is function of space, and in space that means temperature is a function of x, y, z. Temperature is function of x, y, z, right? So let us assume a plane wall. Let us assume a plane wall like this. Let us assume a plane wall like this. Okay. Now this is x direction. This is x direction. This is x direction. This is y direction. This is y direction, and this is the z direction. Okay. This is the x direction. This is the y direction, and this is the z direction. Right. Now temperature in Cartesian coordinate problem, the temperature temperature is function of x direction, y direction, and the z direction, right? That means temperature is a function of space, right? As well as the temperature is function of time, right? And time tau. So in the Cartesian coordinate system, the temperature is a function of x, y, z as well as the time. Because see, here we are talking about the general heat conduction equation, right? And in general heat conduction equation, general, what is the meaning of that general? There are no any assumptions. Getting my point, right? If I say general, that means there are no any assumptions. So we assume the temperature is a function of x, y, z. Maybe in future the temperature is function of x only, or maybe in future the temperature is function of y only. But here we are considering x direction, y direction, and z direction all. Is it fine? As well as the temperature is function of time also. Might be in the problem based on the steady state, the temperature is not function of time, but the problem based on the unsteady, the temperature is a function of time. So again I am telling you guys, here we are dealing with the general heat conduction equation. That's why we are not considering any assumptions. We are not assuming anything. Is it fine? Right. So temperature is function of x, y, z and the time, right? So since it is a crash course, we are not deriving the mathematical expression. I just write the mathematical expression here, right? I'm not deriving it here, right? So what is the general heat conduction equation? What is the general heat conduction equation in Cartesian coordinate? In Cartesian coordinate. So this is del by del x, kx, del t by del x, plus del by del y, ky, del t by del y, plus del by del z, kz, del t by del z, plus q dot g is equal to, that is rho c del t by del tau, right? So that first term, this first term shows the variation of temperature with respect to x. Second term shows the variation of temperature with respect to y. Third term shows the variation of temperature with respect to the z direction. This term shows the internal heat generation term. If let us assume inside the plane wall, internal heat generation occurs. So to incorporate that internal heat generation, that q dot g is here, right? And this term shows the variation of temperature with respect to time. Variation of temperature with respect to time, right? Now what is rho? Rho is the density. Rho is the density of the material, density of the plane wall material. C is the specific heat. What is the C? The C is the specific heat, right? So when you write this mathematical expression, we are not assuming anything. Is it fine? Now I am putting a first assumption here. And what is that assumption? That assumption is material is homogeneous and the isotropic. This is the first assumption. Material is homogeneous and the isotropic. Material is homogeneous and isotropic. So what is the meaning of that? If material is homogeneous and isotropic, that means in every direction, at every point, right, that material properties are same. That means we can say, if material is homogeneous and isotropic, that means we can say that kx is equal to ky is equal to kz is equal to k. So this is the first assumption in the general heat conduction equation, right? The material is homogeneous and the isotropic. So what you are getting, see, that if k is constant, that means it is come out del square t by del x square, del square t by del x square plus del square t by del y square plus del square t by del z square, right? And k is common, right? Plus q dot g is equal to, this is rho c del t by del tau. Fine. Now divide the thermal conductivity both the side. So ultimately you are getting del square t by del x square plus del square t by del y square plus del square t by del z square plus q dot g by k is equal to, this is rho c by k del t by del tau, del t by del tau, del t by del tau. Okay. Now focus on this term, focus on this term, focus on this term. So rho is the property of the material, rho is the property of the material, rho is the density, property of the material, C is the specific heat, property of the material, K thermal conductivity, property of the material. So rho C by K is property of the material, right? If rho is the property of the material, C is the property of the material, K is the property of material, so we can say na ki rho C by K is the property of the material. Is it fine? Right? And the reciprocal of this rho C by K, that means K by rho C, right? This is known as thermal diffusivity. This is also a material property, thermal diffusivity, which is denoted by alpha. So what is the K by rho C? That K by rho C is thermal diffusivity. Is it fine? Right? Now we can write the mathematical expression in this way: del square t by del x square plus del square t by del y square plus del square t by del z square plus q dot g by k is equal to 1 by alpha del t by del tau, 1 by alpha del t by del tau, right? And this is the very popular equation which is known as, Fourier-Biot equation. Fourier-Biot equation, right? And see here the q dot g, right? That q dot g, this q dot g is alpha is thermal diffusivity, K is the thermal conductivity. Now q dot g, this q dot g is volumetric heat generation, volumetric heat generation rate, or rate of volumetric heat generation, or rate of volumetric heat generation, right? And what is the unit? That is watt per meter cube, because that heat generation is a volumetric phenomena. That's why we are taking the volumetric heat generation, right? Heat generation is a volumetric phenomena. If volume is large, then the heat generation will be large. If the volume is less, that heat generation will be less, right? So heat generation, that internal heat generation, is a volumetric phenomena, and that's why here we are considering the volumetric heat generation rate. Is it fine? Right? Now see, can we write this mathematical expression in a vectorial form? right? Can we write this mathematical expression in a factorial form? Yes, we can write, right? Now see, right, in vector calculus, this is the del, this is the operator, okay? In vector calculus, del, this is the del, and this del is I del by del x plus j del by del y plus k del by del z, right? In vector calculus, the del is the Laplacian operator, and we can write the del in this way, that del is equal to I del by del x plus j del by del y plus k del by del z, okay? Now del dot del, this is equal to I del by del x plus j del by del y plus k del by del z, del by del z, right? Dot I del by del x plus j dot del by del y plus k del by del z, okay? Now I dot I, that I dot I is equal to 1, I dot j is equal to 0, I dot k is equal to 0. Now see here, that I dot I 1, so this is del square by del x square, I dot j 0, I dot k 0, j dot I 0, j dot j 1 plus del square by del y square plus, now j dot k 0, k dot I 0, k dot j 0, k dot k 1, del square by del z square, okay? And this is equal to del square. So what is the del square? The del square is del square by del x square plus del square by del y square plus del square by del z square, okay? Now see, now del square dot t is equal to, so this is del square by del x square plus del square by del y square plus del square by del z square dot t. So ultimately what you are getting this del square t by del x square plus del square t by del y square plus del square t by del z square, and this is equal to del square t, okay? Now can we put, instead of this, can we put del square t by del x square plus del square t by del y square plus del square t by del z square as del square t? Yes. So factorial form, general heat conduction equation in factorial form, that is del square t plus q dot g by k is equal to 1 by alpha del t by del tau, right? So this is again Fourier Biot equation, and when you write this mathematical expression, or this mathematical expression, there is only one assumption, and that assumption is material is homogeneous, and isotropic. Material is homogeneous and the isotropic. There is only one assumption, material is homogeneous and isotropic. Okay, now let us discuss some sub cases. Let us discuss some sub cases. So case number 1, or you can say sub case number 1, right? if or I say in case number 1, condition is steady state plus no internal heat generation. No internal heat generation, right? Steady state plus no internal heat generation. So if problem is steady state or condition is steady state, so in steady state that del T by del tau is 0. In steady state that del T by del tau is 0. And if there is no internal heat generation, that means Q dot G is 0. If there is no internal heat generation, then Q dot G is 0. So that general heat conduction equation is reduces in this form, right? Del square T is equal to 0, right? Or we can say del square T by del x square plus del square T by del y square plus del square T by del z square is equal to 0. Is it fine? And this is known as the Laplace equation. Laplace equation. So if condition is a steady state, no internal heat generation is there, then general heat conduction equation is reduces in this form, and this is known as the Laplace equation. This is the Laplace equation. Is it clear? So this is the case number 1. Now come to the case number 2. In case number 2, steady state plus or steady state with internal heat generation. So internal heat generation is there. Steady state plus internal heat generation. So if steady state, that means again del T by del tau is 0 now. And with internal heat generation, that means Q dot G, the rate of volumetric heat generation, that is not equal to 0, right? So that general heat conduction equation is reduces in this form, that is del square T plus Q dot G by K is equal to 0. Is it fine? And this equation is known as Poisson equation. This is the Poisson equation. Right? Or you can write in this way also, del square T plus del square plus del square T plus del y square plus del square T by del z square plus Q dot G by K is equal to 0. Right? Or you can write in this way also. Is it fine? Now, come to the third case. Case number 3. In case number 3, unsteady without internal heat generation. So if there is no internal heat generation, that Q dot G is 0. So general heat conduction equation is reduces in this form. Fine, na? 1 by alpha del T by del tau. Right? The del square T is equal to 1 by alpha del T by del tau. Right? And this equation This equation is known as diffusion equation. This equation is known as diffusion equation, right? Del square T is equal to 1 by alpha del T by del tau, right? And let us assume I'm giving another case number 4. Case number 4. Case number 4. Case number 4. So I'm giving one dimensional. In one dimensional, consider x direction, steady state, with internal heat generation, So can you write the general heat conduction equation, or I can say, can you reduce the general heat conduction equation in a simple form as per the assumptions, as per the condition, right? So one dimensional, that means right, in one dimensional x direction, correct? So one dimensional, so del square T by del x square, del square T by del x square. So del square T by del y square is 0, del square T by del z square is 0, right? So del square T by del x square plus with internal heat generation, so that q dot g term is there, q dot g by k is equal to steady state, so del T by del tau term is 0. Okay, so as per the assumption that one dimensional steady state with internal heat generation, right, the general heat conduction equation is reduces in this form. Okay, so according to the problem, according to the assumptions, you can reduce the general heat conduction equation in a simple form, right? And as per the problem, whatever the ask in the problem, you can proceed. Okay, now in the conduction problems, right, basically in conduction problems, there are two objectives. Please try to understand this concept, right? In conduction heat transfer, basically there are two objectives. And what are those two objectives? That first objective is, in conduction heat transfer, whenever you see the problem based on the conduction heat transfer, so basically there are two objectives. And what are those objectives? That first objective is find the temperature variation. First objective is find the temperature variation, how the temperature is varying, right? How the temperature is varying. So first objective is find the temperature variation, and the second objective is find the rate of conduction heat transfer. Find the rate of conduction heat transfer, right? Please try to understand this. Whenever you are facing the problem based on the conduction heat transfer, so there are two objectives, right? The first objective is find the temperature variation, right? If let us assume the problem is based on the steady state conduction heat transfer, right? So in problem, that how the temperature is changing, how the temperature is varying with respect to the space, right? That you have to find. Or let us assume the problem is based on the unsteady state. So how the temperature is changing with respect to the time, right? So this is the first objective. And the second objective is what is the conduction heat transfer, right? If you know the temperature variation, then you can find out the rate of conduction heat transfer, right? So to understand this part, I am considering a plane wall. So let us assume this is a plain wall, right? And thickness of the plane wall is delta. Thickness of the plane wall is delta. Right? Left face, this is the left face, and left face has temperature T1 and the right face has temperature T2. Okay? Left face temperature is T1, right face temperature is T2. X is equal to 0, so this is the left face. Here that X is equal to 0. Here X is equal to delta. X is equal to delta. And this is the X direction. This is the X direction. Okay? And the thermal conductivity of the wall material, thermal conductivity of the wall material is K. Thermal conductivity of the wall material is K. That cross sectional area is A, and I'm assuming here that T1 is greater than T2. I'm assuming here T1 is greater than the T2. T1 is greater than the T2. Okay, so left face, this is the left face and this is the right face. So left face is maintained at temperature T1, right face is maintained at temperature T2. T1 is greater than T2. So definitely if T1 is greater than T2, right, temperature gradient or temperature del T by del X, right, temperature gradient exists in the X direction. Temperature gradient in the X direction, so definitely within the wall the conduction heat transfer occurs. Within the wall that heat transfer occurs, and what is the mode of heat transfer? Within the wall, what is the mode of heat transfer? That mode of heat transfer is conduction. So let us assume the rate of conduction heat transfer is Q dot. Rate of conduction heat transfer is Q dot. Okay. So what are the assumptions in this problem? So first assumption is material is homogeneous and isotropic. That first assumption is material is homogeneous and isotropic. This is the first assumption. Homogeneous and isotropic. First assumption. The second assumption is one dimensional. Second assumption is a one dimensional, and in one dimensional that is X direction. Second assumption is one dimensional. In one dimensional the direction is X direction. Third assumption is there is no internal heat generation within the wall. Inside the wall there is no internal heat generation, right? No internal heat generation within the wall. No internal heat generation within the wall. No internal heat generation within the wall. Fine. Now next assumption, fourth assumption. That fourth assumption is thermal conductivity is constant. Thermal conductivity is constant. Thermal conductivity is constant. That means thermal conductivity is not changing with respect to temperature, right? Thermal conductivity is constant. Fifth assumption that steady state, right? I already told you that left face temperature is maintained at T1, right face temperature is maintained at T2. T1 is greater than T2. So T1 is not changing with respect to time. T2 is not changing with respect to time. This is our assumption, right? This is our assumption. So temperature is not changing with respect to time. So I can say steady state. Okay. So these are the assumptions that I am considering for this particular problem. Right? Might be in future you are facing a problem where that internal heat generation occurs. Might be in future you are facing a problem where thermal conductivity is not constant. Thermal conductivity is not constant. The thermal conductivity is changing with respect to temperature, right? Or I can say that area is also not, might be in future you are facing a problem where area is not constant. Area is also changing, right? So this is very simple case where we are considering these assumptions. We are considering these assumptions. So in this problem, under these assumptions, I want to find out the how the temperature is changing with respect to space, because steady state is there, na? Steady state is there, so temperature is not changing with respect to time. One dimensional, so temperature is not changing with respect to y, with respect to the z. So here temperature is only function of x. Temperature is only function of x. So how the temperature is changing with respect to x? And once I know the temperature variation with respect to x, then easily I can find out the rate of heat transfer through this plane wall. Okay. Now start from the general heat conduction equation. Start from the general heat conduction equation. General heat conduction equation. General. Start from general heat conduction equation. General heat conduction equation. Now see here. Material is homogeneous and isotropic, so we can write the general heat conduction equation as del square T by del x square plus del square T by del y square plus del square T by del z square plus q dot g by k is equal to 1 by alpha del T by del tau. Del T by del tau. Fine. Now see, one dimensional, and in one dimensional that variation is in x direction. So this term is 0. This term is 0. No internal heat generation is there. So this term is also 0. Right? Steady state. So this term is also 0. So ultimately, that general heat conduction equation is reduces in this form, del square T by del x square is equal to 0. Right? Now integrate this mathematical expression. So when you are integrating it, integrate once. Integrate once. So when you are integrating, the del T by del x is C1. Right? Where C1 is the integration constant. Integrate once again. Integrate once again. Integrate. Integrate once again. So when you are integrating once again, so what you are getting, that T is equal to, that is C1x plus C2. C1x plus C2, where C1 and C2, C1 and C2 are integration constant. Where C1 and C2 are integration constant. Integration constant. And how you calculate the integration constant C1 and C2? How you calculate the integration constant C1 and C2? By using the boundary condition, right? By using the boundary condition. And what are the boundary conditions? First, how many boundary conditions are required? How many boundary conditions are required? So there are two integration constant. There are two integration constant. So if there are two integration constants, so two boundary conditions are required. Two boundary conditions are required. And what are those boundary conditions? That first boundary condition, now see, that first boundary condition at x is equal to 0, see, at x is equal to 0, at x is equal to 0, at x is equal to 0, the t is equal to t1, right? And the second boundary condition is at x is equal to 0, the t is, sorry, at x is equal to delta, sorry, at x is equal to delta, t is equal to t2, right? At x is equal to 0, the T is equal to T1. At x is equal to delta, T is equal to T2. Right. So from these two boundary condition, you can easily find the C1 and C2. You can easily find the C1 and C2. After getting the C1 and C2, after getting the C1 and C2, C1 and the C2, after getting the C1 and C2, right, put here, right, and ultimately what you are getting that T is equal to, or I say T of x is equal to, that is T1 plus T2 minus T1 into x by delta, right? T1 plus T2 minus T1 plus T2 minus T1 into x by delta, right? Find the integration constant by using the boundary conditions, right? Once you find the C1 and C2, put on this mathematical expression, and ultimately you are getting this mathematical expression, that T is equal to T1 plus T2 minus T1 into x by delta. So this mathematical expression shows the variation of temperature with x. Variation of temperature with x. Is it fine? Is it fine? So how the temperature is changing with respect to x? So it is very much clear from this mathematical expression that temperature is changing with respect to x linearly. Linearly. The temperature is changing with respect to x linearly. Okay. So I already told you in conduction heat transfer there are two objectives. The first objective is find the temperature variation, right? So here the temperature variation is linear. Here the temperature variation is linear. Now see the temperature variation. Temperature variation. Here the temperature is T1. Here the temperature is T2. The temperature variation is linear. This is the linear temperature variation. This is the linear temperature variation. Right. Now find out the rate of conduction heat transfer. So to find out the rate of conduction heat transfer, simply use the Fourier law of heat conduction. So from Fourier law of heat conduction, from Fourier law of heat conduction, from Fourier law of heat conduction, that q dot is equal to, that is minus Ka dt by dx. dt by dx. Now find out the dt by dx from here. Find out the dt by dx from here. dt by dx. That dt by dx is equal to, that is T2 minus T1 into 1 by delta. Okay. So rate of conduction heat transfer is equal to, this is K into A minus sign, see minus sign is here. Now it is T2 minus T1 by delta minus, so ultimately you are getting this, na? T1 minus T2, T1 minus T2 by delta. T1 minus T2 by delta. So this is the rate of conduction heat transfer from this plane wall, right? That Ka T1 minus T2 by delta. Is it fine? Is it fine? Yes, sir, it is fine. Okay. Now this is the rate of conduction heat transfer from the plane wall. This is the temperature variation in plane wall under these assumptions. Right? What are the assumptions? Material homogeneous and isotropic, one dimensional, no internal heat generation. And let us assume if there is an internal heat generation, if inside the wall, let us assume there is an internal heat generation. Can we write the same mathematical expression? No, sir. Right? We can't write the same mathematical expression. Why? We can't write the same mathematical expression. Why? Because that general heat conduction equation will change, na? Right? That Q dot G by K, this term is there, na? Is it fine? So this is a very simple case where that assumptions, where we are applying the number of assumptions. Is it fine? Okay. Now, next concept is thermal resistance concept. Okay. Next, we will discuss about the thermal resistance. What is the thermal resistance? And what is the significance of the thermal resistance? Okay. So, next topic is thermal resistance. Okay. Now, next topic is thermal resistance. Right. So, what is the thermal resistance? What is the thermal resistance? Thermal resistance. What is the thermal resistance? What is the thermal resistance? That thermal resistance is resistance against the heat flow, right? That thermal resistance is resistance against the heat flow which is offered by a material, right? So simply we can say thermal resistance, it is resistance, offered by the material. It is resistance offered by the material, offered by the material against the heat flow, against the heat flow, against the heat flow, right? Now in electrical circuit, there is a concept of the electrical resistance. Similarly, in heat transfer there is a concept of thermal resistance, right? So in electrical circuit, there is a concept of electrical resistance. So let us assume there is a wire. Let us assume there is a wire. Okay, and that electrical resistance of the wire, is Re. That electrical resistance of the wire is Re, right? The current which is flowing from this wire is, let us assume, that is I, and the potential difference across the wire is delta V. That potential difference across the wire is delta V, right? So thermal resistance, that is RTH. This thermal resistance is analogous to the electrical resistance, right? Thermal resistance is analogous to the electrical resistance. And how you are calculating the electrical resistance? So we know the Ohm's law, Ohm's law, and as per the Ohm's law, we know that, right? We know that delta V is equal to, this is I Re, right? As per the Ohm's law, we know that the delta V is equal to I Re, and from here we can say that Re is equal to, this is delta V by I, right? And what is the delta V? The delta V is the potential difference, or we can say this is the driving potential for the current. Right? Just take an example for the heat transfer. What is the driving potential? For the heat transfer, what is the driving potential? For heat transfer, the driving potential is the temperature difference. Similarly, for the current flow, what is the driving potential? The driving potential is delta V, right? So thermal resistance is analogous to the electrical resistance. Thermal resistance is analogous to the electrical resistance, right? The current I is the analogous to heat flow, or I can say that heat flow is analogous to the current, and the temperature difference is analogous to, voltage difference. right? So from Ohm's law, we are calculating, the electrical resistance, and similarly, we are calculating the thermal resistance by the analogy, right? So thermal resistance, thermal resistance, that is RTH, is equal to, so instead of the delta V, can I write delta T, and the instead of I, can I write Q dot? Yes, sir, we can write, right? So what is the thermal resistance? The thermal resistance is delta T by Q dot. Okay, and what is the unit? What is the unit? That unit is, what is the unit? That unit is, either you can say Kelvin per watt, or you can say degree Celsius per watt, right? Kelvin per watt, or you can say degree Celsius per watt, right? Kelvin per watt or degree Celsius per watt. So this is the unit of the thermal resistance. Okay, now find out the thermal resistance in different cases. So in case of the plane wall, case number one, in case of plane wall, what is the thermal resistance? So I am considering a plane wall. This is the plane wall, no? This is the plane wall. And I am considering thickness as delta. Here the temperature is T1. Here the temperature is T2. Thermal conductivity is K. Cross sectional area, that is A. And the conduction heat transfer through this plane wall is Q dot. Is it fine? So I want to thermal resistance for this case, right? So as the electrical circuit, we can draw the thermal circuit also here, right? As the electrical circuit, we can draw the thermal circuit also. So this is the thermal resistance which is offered by this plane wall, right? This is the thermal resistance which is offered by the plane wall. Here the temperature is T1. Here the temperature is T2. Thermal resistance is RTH, right? And the heat flow is Q dot. Right? So I want thermal resistance in case, in this case. I want thermal resistance in case of the plane wall. So case number one is the plane wall case, or I can say conduction heat transfer through plane wall case. Conduction heat transfer through plane wall. Right. Now see that Q dot, or we already discussed this, na, that Q dot, what is the rate of conduction heat transfer through this plane wall, and that is Ka T1 minus T2 divided by delta. Yes, sir. Right. And we can write that Q dot like this, T1 minus T2 divided by, this is delta by Ka. Right. This is the equation number 2. So what is the equation number 1? That equation number 1 is Q dot is equal to delta T. From here we can write this, na, delta T divided by RTH. This is the equation number 1. Okay, so compare equation number 1 and equation number 2. Delta T T1 minus T2 divided by RTH. compare the equation number 1 and equation number 2. So from equation number 1 and equation number 2, we can say compare equation 1 and 2. So from equation 1 and equation 2, we can say that RTH, that thermal resistance in case of plane wall, thermal resistance in case of the plane wall, that is equal to, that is delta by Ka. That is delta by Ka. Delta by K. This is the thermal resistance in case of the plane wall. This is the thermal resistance in case of the plane wall. Fine. Similarly, we can find out the thermal resistance in case of the convection heat transfer, and similarly we can find out the thermal resistance in case of the radiation heat transfer also, right? So find the thermal resistance is in case of the convection heat transfer. So that is the case number 2. Case number 2. Case number 2. Case number 2. Convection heat transfer in case of the convection heat, thermal resistance in case of the convection heat transfer. Convection heat transfer. Case number 2. Thermal resistance in case of convection heat transfer. Convection heat transfer. Okay, so I am considering a plate. This is the plate. This is the plate. And let us assume this plate having temperature TW. This plate having temperature TW, right? And over the plate, fluid passes, and fluid having temperature T infinity. Fluid having temperature T infinity, right? And I'm assuming this TW is greater than T infinity. The TW is greater than the T infinity. So what is the rate of convection heat transfer? What is the rate of convection heat transfer? The rate of convection heat transfer is equal to, that is H into A TW minus T infinity. Okay, or we can write in this way also, na? That is TW minus T infinity divided by 1 by HA. 1 by HA. And this is the equation number 3. This is the equation number 3. Okay. Now compare the equation number 1 and the equation number 3. Compare the equation number, compare the equation number 1 and 3. So if you are comparing the equation 1 and the equation 3, so directly we can say that thermal resistance in case of convection heat transfer is equal to 1 by HA. 1 by HA. 1 by HA. So this is the thermal resistance in case of the convection heat transfer. What is the H? That H is the convective heat transfer coefficient. We already discussed. H is the convective heat transfer coefficient. H is the convective heat transfer coefficient. Right. Now next case is case number 3. Thermal resistance in case of the radiation heat transfer. Case number 3. Case number 3. Radiation heat transfer. Radiation heat transfer. Radiation heat transfer. Right. So that we already discussed the radiation heat exchange or radiation heat transfer between the two black bodies. We already discussed now. So let us assume there are two black bodies. Let us assume there are two black bodies. This is the black body number 1. This is the black body number 2. Black body number 1, black body number 1, and this is the black body number 2. Black body having temperature T1, black body 2 having temperature T2, and T1 is greater than T2. T1 is greater than T2. I am assuming this. right? So what is the net radiation heat exchange between these two black bodies? So Q dot is equal to, this is A1 F12 sigma B T1 to the power 4 minus T to the power 4. This mathematical expression I already discussed. Right? Now see, expand this term, right? So that Q dot is A1 F12 sigma B. Now T1 we can write in this way also, na, sigma B T1 square whole square minus T2 square whole square. So A square minus B square. So A square minus B square, A minus B, A plus B. A minus B, A plus B. So this is A plus B and this is A minus B. T1 square minus T2 square. Right? Yes, A square minus B square. So A square minus B square, A plus B, A minus B. Right? Fine. Now again expand this term. So A1 F12 sigma B T1 square plus T2 square, and this is T1 plus T2 and this is T1 minus T2. Fine. So ultimately what you are getting this T1 minus T2, T1 minus T2, right, 1 upon this is A1 F12 sigma B T1 square plus T2 square and T1 plus T2. T1 plus T2. Okay. Now this whole term F12 sigma B T1 square plus T2 square into T1 plus T2 is replaced by the HR, right? Or I can say this whole term is equal to HR. And what is the HR? That HR is the radiative heat transfer coefficient. What is the HR? This HR is radiative heat transfer coefficient. Radiative heat transfer coefficient. So simply we can write that Q dot radiation heat exchange is equal to, this is T1 minus T2 divided by 1 upon HR, and instead of the A1 I am writing A. Right? So simply we can say that rate of radiation heat exchange between two black bodies we can write in this way, that T1 minus T2 divided by 1 upon HR by A. And what is the HR? That HR is the radiative heat transfer coefficient. That HR is radiative heat transfer coefficient. Sometime directly value of HR is given in the problem, right? Directly the radiative heat transfer coefficient is given in the problem. Is it fine? Right? Now see, this is the equation number 4. Now compare equation number 1 and the equation number 4. Compare equation 1 and equation 4. Compare equation 1 and the equation 4. So from comparing the equation 1 and the equation 4, I am getting the thermal resistance in case of the radiation. thermal resistance in case of the radiation, that is 1 upon HRA. And this is analogous to the thermal resistance in case of the convection. In convection, we are using H instead of the HR, right? In convection, we are using the H instead of the HR, right? So this is the convection resistance. This is the convection resistance, and this is the radiation resistance. Okay, so this is the concept of the resistance. This is the concept of the thermal resistance, right? And by using the concept of thermal resistance, we can easily find out the rate of heat transfer. Is it fine? Okay, now next topic is composite wall. Next topic is a composite wall, right? Till the time we are only focused on a single wall, or we can say wall which is made of a single material. Now next topic is a composite wall. And what is a composite wall? If wall is made of more than one material, then that is known as a composite wall, right? And in case of the composite wall, there are three types of connections are possible, right? So first, try to understand composite wall. Composite wall. So what is the composite wall? If wall is made of more than one material, if wall is made of more than one material, then that is known as a composite wall. If wall is made of more than one material, if wall is made of more than one material, that is known as composite wall. That is known as composite wall. That is known as composite wall. Fine. Now, in case of the composite wall, three types of connections are possible. Right? First, series connection. Second one is a parallel connection, and third one is a combination of series and the parallel connection. First one is series connection. First one is series connection, right? Second one is parallel connection. And third one is a combination of both. That means series plus parallel connection. Right? First one is a series connection, second one is a parallel connection, and third one is a combination of series and parallel connection. Right? So first focus on the series connection. Right? So in series connection, that walls are connected side by side, right? In series connection, walls are connected side by side. That means, now see, this is the wall number 1. This is the wall number 1. This is the wall number 2. Okay. Now wall number 1 is made of a material having thermal conductivity K1, right? Wall number 2 is made of a material having thermal conductivity K2, right? Wall number 1 having thickness delta, wall number 1 having thickness delta 1, delta 1, and wall number 2 having thickness delta 2, right? Now left face having temperature T1, here the temperature is T1. Right face having temperature T2, here the temperature is T2. Cross sectional area is A. Cross sectional area is A. Right. So this is a series connection that walls are connected side by side. Walls are connected side by side. Right. So there are two walls, wall number 1 and wall number 2. Wall number 1 having thermal conductivity K1, wall number 2 having thermal conductivity K2, thickness delta 1, delta 2, right? And the temperature difference across the wall is T1 and T1 minus T2, or I can say left face having temperature T1 and the right face having temperature T2, right? And let us assume that intermediate temperature, here the temperature is Ti, right? Here I am assuming there is no thermal contact resistance. What is the meaning of the thermal contact resistance? At the interface, right? Or I can say at the contact surface between the two wall, at the contact surface of the two wall, there is no any resistance. There is no any resistance, right? So thermal contact resistance is negligible, or I can say thermal contact resistance is avoided. Is it fine? Right. Now, first try to understand which type of or which variety of questions are asked in the exam from this particular series connection. Which variety of problems you can say which variety of problem you will face in future when you are solving the problem based on the series connection. Is it fine? Right. Now see, there are variety of problems. I will try to cover all those variety of problems here only, right? So first problem number 1. What is the equivalent thermal resistance? That first question which is asked, what is the equivalent thermal resistance? That first question is, what is the equivalent thermal resistance? This is the first question. The second question is, what is the equivalent thermal conductivity? What is the equivalent thermal conductivity? This is the second question. What is the equivalent thermal conductivity? The third question is, what is the intermediate temperature? Third question is, what is the intermediate temperature? Right. Fourth question is dt by dx, right, or temperature gradient, or I can say relation between theta 1 and theta 2. What is the theta 1? That theta 1 is dt by dx for wall number 1. And what is the theta 2? Theta 2 is dt by dx, temperature gradient in x direction for wall number 2. So what is the relation between the theta 1 and theta 2? Is it fine? Okay. Now try to answer all this question. So first understand the what is the equivalent thermal resistance. Right. what is the equivalent thermal resistance. So that equivalent thermal resistance is the thermal resistance of the equivalent wall. Equivalent thermal resistance is equivalent thermal resistance is thermal resistance offered by the equivalent wall. What is the equivalent wall? What is the equivalent wall? Right. So this is the series connected wall, and equivalent wall for this series connected wall, equivalent wall for this series connected wall is this. This is the equivalent wall. Right? This is the equivalent wall. Right? So this is the wall number 1, this is the wall number 2, this is the equivalent wall, right? And see, what is the temperature here? What is the temperature at the left face? Here the temperature is T1. What is the temperature at the right face? The temperature is T2. What is the thickness here? That is the delta 1. What is the thickness here? That is the delta 2, right? Thermal conductivity is K1. Here the thermal conductivity is K2, and the area is A, right? What is the equivalent wall? That equivalent wall having same cross sectional area, same temperature difference across the left and the right face. This is the left face, this is the right face. Here this is the left face, this is the right face. Here the temperature is T2. So left face and the right face, the temperature difference is same, right? Temperature difference is same. What is the thickness? So that thickness is delta. The thickness is delta, right? And what is the delta? The delta is delta 1 plus delta 2. What is the thickness? The delta is delta 1 plus delta 2. Fine. Now see, what is the rate of conduction heat transfer? What is the rate of conduction heat transfer? So rate of conduction heat transfer through the wall 1 is Q dot 1, through the wall is Q dot 2, through the wall Q dot 1, through the wall 2 is Q dot 2, and across this series connection, the rate of conduction heat transfer is Q dot, right? So what is the relation between Q dot 1, Q dot 2 and Q dot, right? In series connection, what is the relation between Q dot 1, Q dot 2 and Q dot, right? What is the Q dot 1? Rate of conduction heat transfer from the wall number 1. What is the Q dot 2? Rate of conduction heat transfer from the wall number 2. What is the Q dot? That is the rate of conduction heat transfer through complete assembly, right? So what is the relation between Q dot 1, Q dot 2 and the Q dot? So, right. So in series connection, see, in series connection, whatever the conduction heat transfer from the wall number 1, the same rate of conduction heat transfer from the wall number 2, right? So I can say in series connection that Q dot 1 is equal to Q dot 2 is equal to Q dot. We can say na, right? What is the Q dot? Now see, that Q dot is equal to Q dot 1 is equal to Q dot 2. In series connection, the rate of conduction heat transfer is same. The total conduction heat transfer, that is a Q dot, that this Q dot is equal to Q dot 1 is equal to Q dot 2. Is it fine? Is it clear? Is it clear? Is it clear? Right? Now see. Now see, bhai. Now, from this equivalent wall, the rate of conduction heat transfer, that is same as the rate of conduction heat transfer from the composite system, right? This is the equivalent wall. The rate of conduction heat transfer from this equivalent wall is same as the rate of conduction heat transfer from this composite system. Is it fine? Now draw the thermal circuit. If you draw the thermal circuit, in this case, in this case, this is the thermal resistance offered by the wall number 1. This is the thermal resistance offered by the wall number 2. Right. Here the temperature is T1. Here the temperature is T2. Here the temperature is Ti. Thermal resistance offered by the wall number 1 is RTH1. Thermal resistance offered by the wall number 2 is RTH2. Right. Now draw the thermal circuit for the equivalent wall. Thermal resistance for the equivalent wall. Thermal resistance for the equivalent wall. So if you draw the thermal resistance for the equivalent wall, here the temperature is T1, here the temperature is T2, and that equivalent thermal resistance is RTH equivalent. That equivalent thermal resistance is RTH equivalent. Right. Now, okay. What is the thermal conductivity of this equivalent wall? The thermal conductivity of this equivalent wall is K equivalent. The thermal conductivity of this equivalent wall is K equivalent. Right. So that equivalent wall, please try to understand now. Equivalent wall having the same thickness as the composite wall. Equivalent that temperature difference across the equivalent wall is same as the temperature difference across the composite wall. That total heat transfer in equivalent wall is same as the total heat transfer from the composite wall. Right. So question is that what is this equivalent thermal resistance? What is the equivalent thermal resistance and what is the equivalent thermal conductivity? Right. So first find out the equivalent thermal resistance. So to find out the equivalent thermal resistance, I can write, see, that Q dot is equal to, in this case, now see, that Q dot is equal to Q dot, or from here you can write Q dot is equal to T1 minus T2 divided by RTH equivalent. We can write now. For the equivalent wall, see. For the equivalent wall, please see that rate of conduction heat transfer is equal to T1 minus T2 divided by RTH equivalent, or we can say that RTH equivalent is equal to, this is T1 minus T2 divided by Q dot. T1 minus T2 divided by Q dot. Right. Now, we can arrange this term like this also now. T1 minus Ti. T1 minus Ti plus Ti minus T2. Ti minus T2. Right. Divided by Q dot. We can arrange in this way now. There is no problem with that. Right. And also we know that Q dot 1 is equal to Q dot 2 is equal to Q dot. Right. So we can write T1 minus Ti divided by, this is the Q dot 1 plus Ti minus T2 divided by Q dot 2. Why? In series connection, Q dot is equal to Q dot 1 is equal to Q dot 2. In series connection, that Q dot is equal to Q dot 1 is equal to Q dot 2. Whatever the conduction heat transfer from the wall number 1, that is equal to rate of conduction heat transfer from the wall number 2, and that is also equal to rate of conduction heat transfer from the composite wall. Fine. Now see, what is it? what is the thermal resistance? What is the thermal resistance for the wall number 1? What is the thermal resistance for the wall number 1? Can I write in this way? RTH1 is equal to, this is T1 minus Ti divided by RTH1. Sorry, T1 minus Ti divided by Q dot 1. Q dot 1. Can I write RTH1? What is the thermal resistance for the wall number 1? T1 minus Ti by T1 minus Ti by Q dot 1. And what is RTH2? What is the thermal resistance for the wall number 2? So that is Ti minus T2 divided by Q dot 2. Q dot 2. We can write now. RTH1 is T1 minus Ti divided by Q dot 1. And what is the RTH2? That RTH2 is Ti minus T2. Ti minus T2. That intermediate temperature is Ti na. Intermediate temperature is Ti na. Right. So Ti minus T2 divided by Q dot 2. So here we can write, RTH equivalent. That RTH equivalent is equal to, that is RTH1 plus RTH2. That RTH1 plus RTH2. Right. This is RTH1 and this is the RTH2. Clear? So whenever the series connection is there, so what is the RTH equivalent? What is the RTH equivalent? That RTH equivalent is algebraic sum of individual resistance offered by the wall. Right? In case of the series connection, what is the equivalent thermal resistance? That equivalent thermal resistance is algebraic sum, right? Sum of the thermal resistance or sum of the thermal resistance which is offered by the individual wall, right? So RTH equivalent is equal to RTH1 plus RTH2. So in case of the series connection, you can find out the equivalent thermal resistance by this logic. Is it fine? Now find out the, so this is the first question which is asked in the exam, equivalent thermal resistance. So in case of the equivalent thermal resistance is the sum of the thermal resistance offered by the individual wall. Now next is equivalent thermal conductivity. Next one is the equivalent thermal conductivity. Equivalent thermal conductivity. Equivalent thermal conductivity. Find out the equivalent thermal conductivity. K equivalent. Find out the equivalent thermal conductivity, K equivalent. So to find out the equivalent thermal conductivity, we know that equivalent thermal resistance is equal to RTH1 plus RTH2. RTH1 plus RTH2, right? Now what is RTH equivalent? So RTH equivalent is, this is the, what is the RTH equivalent? Now see, what is the RTH equivalent? We can write in this way, na? RTH equivalency, that RTH equivalent is equal to delta by K equivalent in A. Yes or no? What is the RTH1? What is the RTH1? That RTH1 is equal to, delta 1 by K1A. What is the RTH2? What is the RTH2? That RTH2 is delta 2 by K2A. Yes or no? Right, RTH2. Now see, that RTH1 is equal to, this is delta 1 K1A plus RTH2, this is delta 2 K2A. And what is the RTH equivalent? This is delta K equivalent A, right? So A is same, cancel out. So ultimately what you are getting, that delta, so this delta is delta 1 plus delta 2 na, by K equivalent, and that is equal to, this is delta 1 by K1 plus delta 2 by K2. So from here we can find out the K equivalent, that equivalent thermal conductivity. So K equivalent is equal to, this is the delta 1 plus delta 2 divided by delta 1 by K1 plus delta 2 by K2, right? This is the equivalent thermal conductivity. This is the equivalent thermal conductivity. Now let us assume, let us assume that delta 1 is equal to delta 2. Let us assume that delta 1 is equal to delta 2. That means the thickness of the wall is same. Let us assume. So if delta 1 is equal to delta 2, so what is the K equivalent? So that is delta 1 plus delta 2 na? So delta 1 plus delta 2, and that is 2 times of delta 1 we can write. Yes or no? Yes. Delta 1, take a common, and this is 1 by K1 plus 1 by K2. 1 by K1 plus 1 by K2, right? So delta 1 cancel out. So ultimately what you are getting, that K equivalent is equal to, this is K1 K2, so 2 K1 K2. This is 2 K1 K2 upon K1 plus K2. K1 plus K2. So this is the equivalent thermal conductivity. This is the equivalent thermal conductivity, right? Or we can say, what is the conductivity of a equivalent wall? What is the conductivity of a equivalent wall? So conductivity of a equivalent wall is 2 K1 K2 upon K1 plus K2, and this is only applicable when delta 1 is equal to delta 2. This is only applicable when delta 1 is equal to delta 2. Is it fine? Is it fine? Delta 1 is equal to delta 2. There are two walls, right? Two wall, and both the two walls having same thickness. Two walls having same thickness, then this mathematical expression is applicable. Okay, so this is the second question, right? What is the equivalent thermal conductivity? So in this way you can find out the equivalent thermal conductivity. Okay, now come to the next question. What is the third question here? The third question is, what is the intermediate temperature? What is the intermediate temperature? How you are find the intermediate temperature? Third, intermediate temperature. So to find out the intermediate temperature, the series connection is there na? Series connection na? And in case of the series connection, we know na that Q dot 1 is equal to Q dot 2 is equal to Q dot. Yes or no? That Q dot 1 is equal to Q dot 2 is equal to Q dot, right? In case of the series connection. In case of the series connection, that rate of heat transfer, the rate of conduction heat transfer or rate of heat transfer is not a function of X, right? Whatever the conduction heat transfer that occurs from the wall number 1, the same rate of conduction heat transfer occurs from the wall number 2, right? Whatever the rate of conduction heat transfer that occurs from the wall number 1, the same rate of conduction heat transfer occurs from the wall number 2, and the same rate of heat transfer occurs, or same rate of conduction heat transfer occurs from the composite wall, right? So Q dot 1 is equal to Q dot 2 is equal to Q dot. So what is the Q dot 1? We can write T1 minus Ti divided by RTH1. That is equal to, what is Q dot 2? That is Ti minus T2 divided by RTH2. Ti minus T2 divided by RTH2, and that is equal to, what is the Q dot? That Q dot is T1 minus T2 divided by RTH equivalent. And what is the RTH equivalent? Already calculated. What is the RTH equivalent? That RTH equivalent is already calculated. That RTH1 is equal, RTH equivalent is equal to RTH1 plus RTH2. RTH1 plus RTH2. Okay, so in this way you can find out the intermediate temperature. Is it clear? Is it clear? Okay. Now come to the fourth, come to the fourth question, and that question is relation between theta 1 and theta 2. Okay, fine. The relation between theta 1 and the theta 2. What is the relation between theta 1 and theta 2? What is the theta? The theta is temperature gradient in x direction for the wall number 1. And what is the theta 2? The theta 2 is the temperature gradient for wall number 2 in x direction, or you can say that is the slope of the temperature profile also. Slope of the temperature profile also. What is the theta 1 and what is the theta 2? Slope of the temperature profile for the wall number 1, and what is the theta 2? Slope of the temperature profile for the wall number 2. Check. Right. Right. Now see. Now see. This is the composite wall. This is the composite wall. This wall having thickness delta 1. This wall having thickness delta 2. Thermal conductivity K1. Thermal conductivity is K2. Right. Here the rate of conduction heat transfer is Q dot 1. Here the rate of conduction heat transfer is Q dot 2. The total rate of conduction heat transfer is Q dot. Here the temperature is T1 and here the temperature is T2. Right. Now see, for the wall number 1, intermediate temperature is Ti. For the wall number 1, the thermal conductivity is constant na? For the wall number 1, K1 is constant na? Focus on the wall number 1. For the wall number 1, the K1 is constant na? K1 is constant. Right? K1 is not changing na? So what is the temperature profile? The temperature profile is linear. Correct. The temperature profile is linear. This is the temperature profile. Right. Similarly, for the wall number 2, thermal conductivity is constant and that is K2. Again, the temperature variation is like this, linear. Again, the temperature variation is linear and the temperature variation is like this. The temperature variation is like this, right? And the temperature variation is linear. The temperature variation is linear. So here the slope is theta 1. Here the slope is theta 2. Here the slope is theta 2. Here the slope is theta 2. What is theta 1 and what is the theta 2? That is the slope of temperature variation for the wall number 1 and the wall number 2 respectively. Right. So what is the relation between the theta 1 and theta 2? What is the relation between the theta 1 and theta 2? Right. Now see. Now see. That Q dot, I say this Q dot, because we already know that Q dot 1 is equal to Q dot 2 is equal to Q dot. That means we can say this Q dot is not a function of x. We can say na, this Q dot is not a function of x. In x direction, the rate of conduction heat transfer is not changing. Or we can say the rate of conduction heat transfer in x direction is constant na, because Q dot 1 is equal to Q dot 2 is equal to Q dot. Right. Whatever the conduction heat transfer occurs from here, the same rate of conduction heat transfer occurs from here. Right. So rate of conduction heat transfer is not a function of x. Right. Now see, Q dot is equal to, that is Ka dt by dx from the Fourier law of heat conduction. Yes or no? The Q dot is equal to Ka dt by dx. Yes or no? Area is changing with respect to x. Area is changing with respect to x. Yes or no? No sir, area is not changing with respect to x. Here also that area is A, here also that area is A, the cross sectional area. Here also that cross sectional area is A, here also, here also. So again, this A is not a function of x. If Q dot is not a function of x, area is not a function of x, so I can say na, this flux Q dot, this is also not a function of x. That means in x direction the flux is constant, right? So from here we can write this Q dot is equal to, that is K into dt by dx. K into dt by dx. Right. So q dot is not changing with respect to x. Q dot is not changing with respect to x. Q dot is constant. If q dot is constant, that means we can say the product of k and dt by dx is constant. Product of k and dt by dx is constant. Yes or no? Product of k and dt by dx is constant, right? So if k is more, right, and dt by dx, we can say theta, that dt by dx is equal to theta, we can say. So k into theta is equal to constant. Yes or no? K into theta is equal to constant. So if k is more, if k is more, if k is more, then theta will be less, right? Ultimately, there are two variables, x into y is equal to constant. If x into y is equal to constant and x increases, so definitely y should be decreases now. If x increases, then definitely y should be increases, and then only that product of x and y are constant. And similarly, the same thing is here. K theta, k and theta, the product of k and theta are constant, right? So if k increases, theta decreases, right? So without knowing the relation between the k1 and k2, please try to understand. Without knowing the relation between k1 and k2, we can't say relation between the theta 1 and theta 2. If, let us assume, if k1 is greater than k2, if k1 is greater than k2, then theta 1 is lesser than theta 2. If k1 is greater than k2, then theta 1 is lesser than theta 2. If k1 is lesser than k2, then theta 1 is greater than theta 2. This is the relation. This is the relation. Is it fine? Right. So relation between theta 1 and theta 2, you can find out if you know the relation between k1 and k2. Otherwise, you can't. Is it fine? Is it clear? Okay. Now, next case. Now see the next case. Now see the next case. I think not next case. This is a question number 3. This is question number 3 and this is question number 4. No? This is question number 4. Question number 4. Now come to the question number 5. Now come to the question number 5. Question number 5. Now see, I am considering a wall here. I am considering a wall here. Okay, I am considering a wall here. Okay. Now, in this side, there is a hot fluid. In this side, there is a hot fluid. In this side, there is a hot fluid. In this side, there is a cold fluid. Cold fluid. So I am showing cold fluid by blue color. Cold fluid. Cold fluid. Right? Thickness of this wall is delta. Cross sectional area is A. Cross sectional area is A. And the thermal conductivity of this wall is K. Thermal conductivity of this wall is K. Hot fluid having temperature TH. Cold fluid having temperature Tc. Cold fluid having temperature Tc. Cold fluid having temperature Tc. Convective heat transfer coefficient on cold fluid side is Hc, and the convective heat transfer coefficient on hot fluid side, that is Hh. Right? This wall having temperature T1, this wall having temperature T1, this wall having temperature T2. Right? TH is greater than the Tc. I am assuming that TH is greater than Tc. This is a hot fluid, this is a cold fluid. TH is greater than TC, right? Now TH is greater than TC, so the rate of heat transfer, occurs. The rate of heat transfer occurs, yes or no? The rate of heat transfer occurs from the hot fluid to the cold fluid. From the hot fluid to the cold fluid, yes or no? Yes, sir. Yes, sir. The rate of heat transfer occurs from the hot fluid to the cold fluid, right? So if I ask you what is the mode of heat transfer from the hot fluid to the left face of the wall? What is the mode of heat transfer from the hot fluid to the left face of the wall? What is the mode of heat transfer? So that mode of heat transfer is a conduction, right? What is the mode of heat transfer within the wall? That is conduction. And what is the mode of heat transfer from right face of the wall to the cold fluid? That is a convection, right? Radiation we are neglected right now. Radiation heat transfer we are neglected right now, right? So from hot fluid to the left face of the wall, this is the left face of the wall, this is the right face of the wall. So hot fluid to the left face of the wall, that mode of heat transfer is convection. So let us assume the convection heat transfer is Q dot 1. The convection heat transfer is Q dot 1. Within this solid wall, the rate of heat transfer or mode of heat transfer is conduction, and that conduction heat transfer is Q dot 2. From the right face of the wall to the cold fluid, the rate of conduction heat transfer is Q dot 3. Rate of convection heat transfer is Q dot 3. From the right face to the cold fluid, what is the mode of heat transfer? That is a convection. And what is the convection heat transfer? That is a Q dot 3. If I ask you what is the relation between Q dot 1, Q dot 2, Q dot 3 and the Q dot, right? So first try to understand this is a series connection. Yes or no? This is the series connection, yes or no? Whatever the convection from the hot fluid side, that is equal to the conduction in the wall, that is equal to the convection heat transfer, right? Convection heat transfer on cold fluid side, right? So Q dot 1 is equal to Q dot 2 is equal to Q dot 3 is equal to Q dot, yes or no? Right? Please try to understand now that total heat transfer is Q dot. Whatever the convection, right, on hot fluid side, that Q dot 1 is equal to Q dot 2 is equal to Q dot 3 is equal to Q dot, right? So Q dot 1 is equal to Q dot 2 is equal to Q dot 3 is equal to Q dot, yes or no? Right? Now see, if I ask you draw the thermal circuit, are you able to draw the thermal circuit? Yes sir, we are able to draw the thermal circuit. Now see, first there is a convection resistance, then there is a conduction resistance, then there is a convection resistance. This is the convection resistance on hot fluid side, conduction resistance within the wall, convection resistance on cold fluid side. Here the temperature is TH, here the temperature is TC, here the temperature is T1, here the temperature is T2, right? Thermal resistance 1, thermal resistance 2, thermal resistance 3. What is the RTH1? What is the RTH1? That RTH1 is equal to, this is 1 upon HHA. What is the RTH2? What is the RTH2? That RTH2 is equal to delta divided by Ka. What is the RTH3? RTH3, that RTH3 is equal to, that is 1 upon HC by A. So what is the RTH equivalent? Series connection is there, na? Series connection. So what is the RTH equivalent? That RTH equivalent is equal to, this is RTH1 plus RTH2 plus RTH3, right? So simply we can say 1 upon HHA plus delta by Ka plus 1 upon HCA, right? And this is the equivalent thermal resistance. Is it fine? Right? And also we can write that Q dot is equal to Q dot 1 is equal to Q dot 2, right? What is the Q dot 1? Q dot 1 is equal to Q dot 2 is equal to Q dot 3. What is the Q dot 1? This is TH minus TC divided by RTH equivalent, right? This is equal to Q dot 1 TH minus T1 divided by RTH1. What is the Q dot 2? T1 minus T2 divided by RTH2, right? And what is the Q dot 3? This is T2 minus T3 divided by this is RTH3, right? So this is the energy balance. This is the energy balance, right? If you want to see the temperature profile, in this case, can we draw the temperature profile in this case? Can we draw the temperature profile on this case? Yes, definitely we can draw, right? Definitely we can draw. So temperature profile in this case, see, hot fluid temperature TH, and suddenly here the temperature drops to T1, right? Then within the wall, the temperature variation is linear. Now, here the temperature is Tc, na? This temperature is Tc. This temperature is Tc. Now see, this temperature is Tc. Here the temperature is T1. Now again, the temperature drop like this. Not linear. The temperature drop like this. Like this. Right? So this is TH. This is Tc, right? Here the temperature is T1, here the temperature is T2. This is the temperature profile. Why there is sudden drop? Why this is not a linear drop, right? That this concept we will discuss in the convection. There is a concept of the thermal boundary layer. Right? This part we will discuss in the convection Wallah topic, in convection chapter. Is it fine? Right? So this is all about the series connection. In series connection, that variety of problems, right? I already discussed variety of problems, right? In some question that equivalent thermal resistance asked, in some question equivalent conductivity asked, intermediate temperature asked, or relation between theta 1 and theta 2, right? So what is the equivalent thermal resistance? In case of the series connection, what is the equivalent thermal resistance? That algebraic sum of the individual thermal resistance of the wall. What is the K equivalent? What is the equivalent thermal conductivity, right? So equivalent thermal resistance, equivalent wall, that is the thermal resistance offered by the equivalent wall, or I can say equivalent thermal conductivity. That equivalent thermal conductivity is equivalent thermal conductivity is thermal conductivity of the equivalent wall. And what is the equivalent wall, right? That equivalent wall, what is the equivalent wall? That equivalent wall, this is the equivalent wall, right? This is the series connection wall. So equivalent to this wall, this is the wall, right? Equivalent to this, that is the wall. This is the equivalent wall, right? And the equivalent wall having thermal resistance, that is a RTH equivalent, and the equivalent wall having the thermal conductivity K equivalent, right? And this equivalent wall in such a way, the temperature difference across the left face, right face will be same as the composite wall, I can say, right? The thickness is same as total thickness of this composite wall. Cross sectional area will be same. Temperature difference across the left face and right face will be same. The rate of conduction heat transfer will be same. So what is the thermal resistance? What is the equivalent thermal resistance, and what is the equivalent thermal conductivity, right? So that equivalent thermal resistance is individual sum of the individual sum of the thermal resistance offered by the individual wall, right? Equivalent thermal conductivity, by using this concept you can find out the equivalent thermal conductivity. If the thickness of the wall is same, if thickness of the wall is same, then we can say 2k1 k2 upon k1 plus k2. How you find the intermediate temperature? That intermediate temperature is find out by using the energy balance, right? The q dot 1 is equal to q dot 2 is equal to q dot. What is the q dot 1? T1 minus Ti by RTH1, right? You can write this now. What is the q dot 2? Ti minus T2 divided by RTH2. And what is the q dot? The q dot is T1 minus T2 divided by RTH equivalent, right? So by using this energy balance you can find out the intermediate temperature, right? Now next question that is asked in the exam, relation between theta 1 and theta 2. So how you can find out the relation between theta and theta 2, right? If you know the relation between k1 and k2, then you can easily comment on the theta 1 and theta 2, right? So already I discussed that rate of heat transfer is not changing with respect to x, rate of heat transfer is constant in x direction, right? So flux is also constant because area is also constant, no? So k into dt by dx, or I can say k or theta, product of k and theta is constant. So if k increases, theta decreases. So for a wall, if k is more, then theta will be less, right? And this is the next variety of problem which is asked in the exam, right? This is the next variety of problem, right? So this is all about the series connection. Okay, now next is the parallel connection. Now next is the parallel connection. Parallel connection. So in series connection, walls are placed side by side, correct? In series connection, walls are placed side by side, whereas in parallel connection, walls are placed one over to another, right? One over to another. Now see, so I am showing a parallel connection here. So I am considering two walls, and these two walls are in parallel connection. Okay, so let us assume this is the wall number 1, this is the wall number 2. Wall number 1 having thermal conductivity K1, wall number 2 having thermal conductivity K2, and the cross sectional area for the wall number 1 is A1 and for the wall number 2 is A2. Thickness of both the wall is same, so delta 1 is equal to delta 2. Now this face, this is the left face, this is the left face, this is the right face. Left face is maintained, this left face, na? This is the left face, correct? This left face is maintained at a temperature T1. This left face is maintained at a temperature T1, and the right face is maintained at a temperature T2. And again I am assuming T1 is greater than the T2. T1 is greater than the 2T. Okay. Now the rate of conduction heat transfer from the wall number 1 is q dot 1 and the rate of conduction heat transfer from the wall number 2 is q dot 2. Okay, and the total heat transfer from this composite wall is q dot. The total heat transfer from this composite wall is q dot. So q dot is the total heat transfer through this composite wall. So what is the relation between q dot 1 and the q dot 2? What is the relation? So q dot is equal to, we can write q dot 1 plus q dot 2. In series connection, in series connection, that q dot is equal to q dot 1 plus, sorry, in series connection, q dot is equal to q dot 1 is equal to q dot 2, and so on. Whereas in parallel connection, that q dot, the total heat transfer, the total rate of conduction heat transfer is equal to q dot 1 plus q dot 2. Is it fine? Right. So again, there are certain number of question, right, which is asked in the parallel connection, right? And what are those what are those questions, right? That first question is equivalent thermal resistance. Okay, remember in the parallel connection also we were calculated the equivalent thermal resistance. Okay, same thing. So first question, in parallel connection, what is the equivalent, thermal resistance? Equivalent thermal resistance. What is the equivalent thermal resistance? Okay. Now, what is the second question? The second question is equivalent thermal conductivity. The second question is equivalent thermal conductivity, right? Third question. Third question. Third question is relation between theta 1 and theta 2. What is the theta 1? What is the theta 2? You know very well. Relation between theta 1 and the theta 2, right? So theta 1 is the slope of temperature profile for the wall number 1, and theta 2 is the slope of temperature profile for the wall number 2. Is it fine? Right. Now see, first understand what is the equivalent wall. That equivalent wall concept we already discussed in the series connection. If this parallel connected wall is replaced through a single wall, right? This is a composite wall. This wall is made of more than one material. है ना? So if this parallel connected wall or this composite wall is replaced through a single wall in such a way that temperature difference across the left face and the right face is same, right? The total heat transfer rate is same, right? Delta 1 thickness is same and the cross sectional area is same, right? So that wall is known as the equivalent wall, right? So are you able to draw a equivalent wall? Are you able to draw the equivalent wall? Yes sir, bilkul. Now see, so this is your parallel connected wall. This is parallel connected wall. Just 1 minute. Okay, this is a parallel connected wall. Okay. Now, thickness delta 1 is equal to delta 2. This is wall number 1. This is wall number 2. Wall number 1 having thermal conductivity K1. Wall number 2 having thermal conductivity K2. This face having temperature T1. This face having temperature T2. Right. So, this parallel connected wall, this composite wall is replaced through a single wall. So this is the single wall. Okay. Okay. So this composite wall is replaced through a single wall in such a way that temperature difference across the wall is same. So left face has a temperature T1, right face has a temperature T2. Right. This equivalent wall has thickness delta. Cross sectional area is A, right? And the thermal conductivity is K equivalent. Right. So what is the equivalent wall? That equivalent wall, what is the equivalent wall? Right. This composite wall is replaced by the equivalent wall in such a way that temperature difference across the wall will be same, right? The thickness will be same, cross sectional area will be same, and the total heat transfer, the total heat transfer from this composite wall, what is the total heat transfer? The total heat transfer is q dot na. The total heat transfer is q dot, yes or no? The total heat transfer is q dot, right? The same rate of conduction heat transfer occurs from this wall also, q dot, right? So this equivalent wall thermal conductivity is K equivalent, right? And thermal resistance offered by this equivalent wall is RTH equivalent. So can you draw the thermal circuit? Can you draw the thermal circuit? Yes, sir, definitely we can draw the thermal circuit. Now see. So this is the thermal circuit for this equivalent wall. What is the temperature here? The temperature is T1. What is the temperature here? The temperature is T2. This is the RTH equivalent. Okay. Now draw the thermal circuit for this composite wall. So the rate of conduction heat transfer from the wall number 1 is Q dot 1, from the wall number 2 is Q dot 2. Now draw the thermal circuit. So this is the thermal resistance offered by the wall number 1. This is the thermal resistance offered by the wall number 2. Okay, and both are connected in parallel. Both are connected in parallel. So this is the thermal resistance offered by the wall number 1, and this is the thermal resistance offered by the wall number 2, right? And temperature is T1 here, and here the temperature is T2. The rate of conduction heat transfer from this wall is Q dot 1, wall number 1 is Q dot 1, and from wall number 2 is Q dot 2, right? And we know that in parallel connection that Q dot is equal to Q dot 1 plus Q dot 2. Okay, now the first question is find the equivalent thermal resistance. The first question is find the equivalent thermal resistance. So equivalent thermal resistance, first equivalent thermal resistance. Equivalent thermal resistance, RTH equivalent, right? So it is clear from parallel connection that Q dot is equal to Q dot 1 plus Q dot 2. Fine, na? Right? Q dot 1 is equal to Q dot 2, and we know that Q dot is equal to, we can write in this way, that delta T divided by RTH. Yes or no? Yes, sir. So what is the Q dot? That Q dot, can we write that Q dot in this way, that Q dot is equal to the temperature difference across the equivalent wall is T1 minus T2. So can we write in this way, that Q dot is equal to, this is T1 minus T2, T1 minus T2 by RTH equivalent. RTH equivalent, and this is equal to, what is the Q dot 1? That Q dot 1 is T1 minus T2. See, what is the Q dot 1? The Q dot 1. Q dot 1, what is the temperature here? That is T1. No? Here, that for the wall number 1, the temperature is here T1. Here the temperature is T2. Right? For wall number 2, here the temperature is T1. Here the temperature is T2. Is that fine? So, T1 minus T2 by RTH1 plus, what is the Q dot 2? This is plus T1 minus T2 by RTH2. RTH2. Fine. Now, it is clear, T1 minus T2, T1 minus T2, T1 minus T2 cancel from both the side. So, ultimately, what you are getting, 1 by RTH equivalent is equal to 1 by RTH1 plus 1 by RTH2 and so on. Right? If number of walls are more than 2, then it is 1 by RTH1 plus 1 by RTH2 plus 1 by RTH3 plus 1 by RTH4 is equal to 1 by RTH equivalent. Right? So, if walls are connected, in parallel, then you can find the equivalent thermal resistance by using this mathematical expression. Right? In series connection, it is RTH equivalent is equal to RTH1 plus RTH2 plus RTH3 and so on. In case of the parallel connection, right, that 1 by RTH equivalent is equal to 1 by RTH1 plus 1 by RTH2 plus 1 by RTH3 and the so on. Fine. Now, so this is the first question. Now come to the second question. The second question is, find the equivalent thermal conductivity. Find the equivalent thermal conductivity. Equivalent thermal conductivity. Equivalent thermal conductivity. K equivalent. Right. So, equivalent thermal conductivity is a thermal conductivity of equivalent wall. Right. Now, to find out the equivalent thermal conductivity, we already discussed 1 by RTH, 1 by RTH equivalent is equal to 1 by RTH1 plus 1 by RTH2. Is it fine? Right. Now, what is RTH1? What is the RTH1? That RTH1 is equal to, this is the delta 1 by K1A, right? K1A1, sorry. What is the RTH2? RTH2, that is delta 2 by K2A2. And what is the RTH equivalent? What is the RTH equivalent? That is equal to delta by K equivalent A. Right. Now, so 1 by RTH equivalent. So 1 by RTH equivalent. What is the RTH equivalent? Delta by K equivalent. Hai na? That is delta by K equivalent A is equal to 1 by that is delta 1 K1 A1 plus 1 by delta 2 K2 A2. Right. So, we know that delta 1 is equal to delta 2, correct? Delta 1 is equal to delta 2. So, we can write in this way also. This is the K equivalent. K equivalent A by delta is equal to K1 A1 delta 1 plus K2 A2 delta 2, right? And we know that delta 1 is equal to delta 2 is equal to delta, right? So ultimately what you are getting, that K equivalent is equal to K1 A1 plus K2 A2 divided by A, right? And this is the K equivalent. This is the K equivalent, right? Now, if I'm assuming A1 is equal to A2, A1 is equal to A2, if I'm assuming that A1 is equal to A2, A1 is equal to A2, then what I'm getting, K equivalent is equal to K1 A1. So A1 is equal to A2 na. So this is A1 K1 plus K2, and that A is A1 plus A2. So this is 2 times of A1. A1 cancel out. So K equivalent is K1 plus K2 by 2. Right. So this is the equivalent. This is the equivalent thermal conductivity. This is the equivalent thermal conductivity if two walls having same cross sectional area. Two walls having same cross sectional area. Two walls having same cross sectional area. If two walls having same cross sectional area, then K equivalent is K1 plus K2 by 2. Okay, fine. Now, next is, what is the relation between theta 1 and theta 2? Relation between theta 1 and the theta 2. Theta 1 and theta 2. What is the theta 1? That theta 1 is del T by del X for the wall number 1. And what is the theta 2? That theta 2 is dt by dx for the wall number 2. Is it fine? Is it fine? Now see, for the wall number 1, the thermal conductivity is constant, which is K1. For wall number 2, the thermal conductivity is constant, which is K2, right? If K1 is constant, if thermal conductivity is constant, then the temperature variation is linear. So simply we can write that delta T is T1 minus T2 divided by, what is the thickness for the wall number 1? That is delta 1. For the wall number 2, what is dt? T1 minus T2. And what is thickness? That is delta 2. And we know that delta 1 is equal to delta 2. Delta 1 is equal to delta 2. See the diagram? That delta 1 is equal to delta 2. So if delta 1 is equal to delta 2, then it is very much clear, right, that theta 1 is equal to theta 2. That theta 1 is equal to theta 2. Theta 1 is equal to theta 2. That means if you draw the temperature profile, now see, the temperature profile is linear. Here also the temperature profile is linear, right? This angle, this is a slope now. This is a slope now. This is theta 1. Now here this is the slope now. This is theta 2. So theta 1 is equal to theta 2. Theta 1 is equal to theta 2. Is it fine? Right. Now come to the next question. So question number 1, question number 2, question number 3. Now question number 4. Question number 4. I am considering parallel connected plane wall. parallel connected plane wall. Parallel connected plane wall. Okay. On this side there is a hot fluid. On this side there is a hot fluid. Hot fluid. On this side there is a cold fluid. Cold fluid. Right. Hot fluid having temperature TH. Convective heat transfer coefficient is HH. Cold fluid having temperature TC. And the convective heat transfer coefficient, that is HC. Right. And the temperature of the left face of the wall, temperature of left face of the wall is T1. Here the temperature is T1 and here the temperature is T2. Here the temperature is T2. Okay, and definitely TH is greater than TC. TH is greater than TC. TH is greater than TC. Right. Now my question, acha, just 1 minute. Wall number 1, wall number 2, wall number 1 having thermal conductivity K1, wall number 2 having thermal conductivity K2, thickness delta 1 is equal to delta 2. Fine. Now, are you able to find out the equivalent thermal resistance for this configuration? Are you able to find out the equivalent thermal resistance for this configuration? So first draw the thermal circuit. So if you draw the thermal circuit, see, from the hot fluid to the left face of the wall. This is the left face of the wall. This is the right face of the wall. So from the hot fluid to the left face of the wall, what is the mode of heat transfer? That is a convection. So there is a convection resistance, right? From the hot fluid to the left side of the wall, the mode of heat transfer is convection. So there is a convection resistance. In wall number 1, conduction heat transfer occurs. So there is a conduction resistance. In wall number 2, there is a conduction heat transfer. So there is again conduction resistance. And from the right face of the wall to the cold fluid, that mode of heat transfer is convection. So there is a convection resistance. Is it fine? So are you able to draw the thermal circuit? Yes, sir. We are able to draw the thermal circuit. And first, there is convection resistance on hot fluid side. Then there is conduction resistance of the wall number 1. Then there is a conduction resistance for the wall number 2. Right. Then there is convection resistance on the cold fluid side. Convection resistance on the cold fluid side. Okay. So this is the RTHH. This is a hot fluid side convection resistance. This is cold fluid side convection resistance. This is the thermal resistance offered by the wall number 1. This is the thermal resistance offered by the wall number 2. Right. Here the temperature is TH. Here the temperature is T1. Here the temperature is T2. Here the temperature is TC. Okay, so this is basically combination of series and parallel connection. Basically, this case is a combination of series and parallel connection, right? Because wall number 1 and wall number 2 are connected in parallel. Wall number 1 and wall number 2 are connected in parallel, right? And wall number, that hot fluid, this composite wall and the cold fluid, that is connected in series. So basically, this is the problem where the series and parallel connection both are used, right? So in such type of problem, first find out the equivalent thermal resistance. First find out the equivalent thermal resistance for this parallel connection, right? That means first replace the parallel connected wall. First replace the parallel connected wall first replace the parallel connected wall through a single wall, which is the equivalent wall. First, replace the parallel connected wall through a single wall, which is the equivalent wall, and then that hot fluid wall and the cold fluid are in series, side by side, na? Is it fine? Is it fine? So what is the equivalent thermal resistance for the wall number 1 and wall number 2? So equivalent thermal resistance we can write in this way: 1 by RTH12. See, 1 by RTH12. So this is the equivalent thermal resistance of wall number 1 and wall number 2. This is equal to 1 by RTH1 plus 1 by RTH2. Right? In this way, we can find out the RTH12. So what is RTH12? That RTH12 is equivalent thermal resistance of wall 1 and the wall 2. Wall 1 and the wall 2. Is it fine? Now, when you are getting the RTH12, again draw the thermal circuit. So this is for convection resistance on hot fluid side, conduction resistance of the equivalent wall or equivalent thermal resistance, and this is the convection resistance on cold fluid side. So this is the thermal resistance, equivalent thermal resistance for the wall 1 and wall 2. And this is thermal resistance for the thermal resistance on the cold fluid side. So this is RTHH, this is RTH12, and this is RTH, thermal resistance on the cold fluid side. Here the temperature is T1, sorry, TH. Here the temperature is T1, here the temperature is T2, and here the temperature is TC. Right? Now it is very much clear. It is very much clear. All the resistances are in series. All the resistances are in series. If resistances are in series, then how already we find na? Okay, already we find the equivalent thermal resistance, right? So in this case, that equivalent thermal resistance, 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 RTH equivalent is equal to, right? So this is series connection, na? So if this is a series connection, then RTHH plus RTH12 plus RTHC. Right? In this way, we can find out the equivalent thermal resistance, complete or I can say total equivalent thermal resistance. Is it clear? Okay. Now, are you able to do energy balance? Are you able to do energy balance? Yes. Yes, sir. Energy balance. So from energy balance, we can write now that Q dot 1, this is the rate of conduction, this is the rate of convection heat transfer from hot fluid side. See, Q dot 1, or I can say Q dot H, hot fluid side convection heat transfer from this wall number 1, the rate of conduction heat transfer is q dot 1. For the wall number 2, the rate of conduction heat transfer is q dot 2. And the cold fluid side, that convection heat transfer is q dot c. Right. So from energy balance, we can write q dot h is equal to q dot c. And what is the q dot? This q dot is equal to sum of q dot 1 plus q dot 2. Sum of q dot 1 plus q dot 2. Right. So we can write q dot h. That q dot h is th minus t1 divided by rthh. Right. Now q dot, this q dot is T1 minus T2, and this is the equivalent thermal resistance of wall 1 and 2, and next q dot c. So that q dot c is T2 minus Tc, rthc. Right. So from this energy balance, if T1 is unknown, we can find out the T1 easily. If T2 is unknown, we can find out the T2 easily. Right. So whatever is unknown, we can find the that unknown. Okay. So this is a simple energy balance. So I hope each and everything is clear. So this is all about the parallel connection. Is it fine? Okay. Now come to the next topic, which is a plane wall with internal heat generation. So far, we are not considering the internal heat generation, right? So far, we are not considering the internal heat generation. We are considering simply there is a plane wall. And in that plane wall, there is no internal heat generation. But before that, we will discuss another case, that plane wall with variable thermal conductivity. And after that, we will discuss the plane wall with internal heat generation. Right. So first we will discuss the plane wall with variable thermal conductivity. Plane wall with variable thermal conductivity. Plane wall with variable thermal conductivity. With variable thermal conductivity. Plane wall with variable thermal conductivity. Right. Plane wall with variable thermal conductivity. So far, we are not considering the variable thermal conductivity. We are assuming the thermal conductivity is constant. Right. Now, in this case, we are considering that variable conductivity is not constant, that variable conductivity is a function of temperature. That variable thermal conductivity is function of temperature. So, plane wall with variable thermal conductivity. So, I already told you, in the conduction heat transfer, there are two objectives. In conduction heat transfer, there are two objectives. The first objective is find the temperature variation, and the second objective is find the rate of conduction heat transfer. Is it fine? So here we are finding both the things, temperature variation as well as the rate of conduction heat transfer. Right. Now see, let us assume the thermal conductivity changing with respect to temperature by following this equation. So K is equal to K naught 1 plus beta T. Let us assume. Okay. Maybe in future you are getting the variation of thermal conductivity like this. K is equal to K naught 1 plus beta T plus alpha T square. Is it fine? So I'm assuming that thermal conductivity is linearly changing with respect to temperature. The K is equal to K naught 1 plus beta T. Okay, so this is a plane wall. I'm talking about this plane wall only, na? This is a plane wall. This is the plane wall. This is the plane wall. And this plane wall having thickness delta. Check. This is x direction. And at x is equal to 0, the temperature is T1. And at x is equal to delta, the temperature is T2. Right? That cross-sectional area is A. Cross-sectional area is A. And that thermal conductivity K is equal to, I'm assuming K naught 1 plus beta T. Right? Where K naught is constant, which is thermal conductivity at 0 degrees Celsius. K naught is constant, which is thermal conductivity, thermal conductivity at 0 degree Celsius. Thermal conductivity is 0 degree Celsius. And beta, that is also constant. Beta is also constant. That depends on type of the material. That depends on the type of the material. What is the meaning of that? That means value of beta may be positive. That value of beta may be positive. That value of beta may be negative, or that value of beta may be 0. So if that value of beta is equal to 0, if value of beta is equal to 0, that means thermal conductivity is not changing with respect to temperature. If thermal conductivity is positive, if beta is positive, if beta is 0, that means thermal conductivity is not changing with respect to temperature. If beta is positive, then as temperature increases, thermal conductivity increases. And beta is negative. If beta is negative, then if temperature increases, thermal conductivity decreases. Is that clear? Right. Now see, I am considering all three cases. If beta is positive, right, then what is the temperature profile? If beta is 0, then what is the temperature profile? If beta is negative, then what is the temperature profile? If beta is 0, we already know that temperature profile is linear, because if beta is 0, then thermal conductivity is constant. If thermal conductivity is constant, right, no internal heat generation, steady state condition, one dimensional, these are the assumptions then that temperature profile is linear, right? So what are the assumptions? That assumptions are also very, very important now. Assumptions are also very, very important, right? So material is homogeneous and the isotropic, that is a common assumption. So I am not writing again and again. Material is homogeneous and isotropic, right? What are the main assumptions? What are the main assumptions? What are the main assumptions? That first assumption is one dimensional. In one dimensional, I am considering x direction. Right, first thing. Second, steady state. Wall temperature is maintaining at temperature T1 and T2 throughout the time. Steady state. Third, no internal heat generation within the wall. No internal heat generation within the wall. No internal heat generation within the wall. Fourth assumption. That fourth assumption is thermal conductivity is function of temperature. Thermal conductivity is function of temperature, which is already discussed. The thermal conductivity is not constant, that is a function of temperature. And I am assuming that the thermal conductivity varies, linearly varies with temperature. I am assuming this. right? Most of the material follows this relation only. Most of the material follows this relation only. K is equal to K naught 1 plus beta T. Okay. Now see. Now let's start our discussion on temperature profile. How the temperature changing with respect to X. Because if, see, if beta is 0, then what is the temperature profile? The temperature profile is linear under these assumptions. If beta is 0, so case number 1, I am considering case number 1. Case number 1. Case number 1. If beta is 0, so if beta is 0, that means K is equal to K naught. That means thermal conductivity is constant, na? Thermal conductivity is not function of temperature. Yes or no? Thermal conductivity is not function of temperature. Thermal conductivity is not function of temperature. And in this case, we already know that temperature varies linearly with X. Okay, so this is the X direction. The temperature is T1. This phase has temperature T1. This phase has temperature T2. And the temperature varies linearly. Like this. Temperature varies linearly. So there is no problem with that. We already discussed this part. Now, come to the case number 2. Case number 2. In case number 2, I am considering beta is positive. So if beta is positive, that means K is equal to, K naught 1 plus beta T. K is equal to K naught 1 plus beta T. Now see, again I am considering this wall only. Right, now the temperature of the left face is T1, temperature of the right face is T2. Fine, this is the X direction. Okay, now see, left phase has a temperature T1, right phase has a temperature T2. The rate of conduction heat transfer is Q dot, yes or no? Yes, sir. What is the cross-sectional area? The cross-sectional area is A. Now my question to you, that Q dot, the rate of conduction heat transfer, is a function of X. The rate of conduction heat transfer is a function of X. Tell me guys, the rate of conduction heat transfer is a function of X or not? So answer is, the rate of conduction heat transfer is not a function of X, right? Now see, from this location, what is the rate of conduction heat transfer? Q dot. From this location, what is the rate of conduction heat transfer? That is a Q dot. From this location, the rate of conduction heat transfer is Q dot, right? So Q dot is not a function of X. This is like a series connection only, na? That small plane walls are connected in series, side by side. Small plane walls are connected side by side. It is like a series connection, right? So this Q dot is not a function of X. Q dot is not changing with respect to X. At any X, the rate of conduction heat transfer is Q dot only, right? So Q dot is not a function of X. A is a function of X? No. For this particular location, what is the cross-sectional area? What is the area which is normal to the direction of conduction heat transfer? That is A only. For this space also, for this location also, what is the area which is normal to the conduction heat transfer? That is A only. So A is also not a function of X. So Q dot is not a function of X. Q dot is not a function of x. A is not a function of x. A is not a function of x. So we can say that Q dot, which is a flux, that means Q dot by A, is also not a function of x. That flux is not a function of x. That means in x direction, Q dot is constant. In x direction, Q dot flux is constant. Tell me guys, yes or no? Yes sir, absolutely correct. Now from the Fourier law of heat conduction, we know that from the Fourier law of heat conduction, from the Fourier's law of heat conduction, right? We know that Q dot, or simply we can write in form of the flux also, that Q dot is equal to minus K dt by dx. Minus K dt by dx. Right? And what is the dt by dx? We know that the dt by dx is the slope of the temperature profile. Temperature gradient in x direction. Slope of the temperature profile. Is it fine? Now see, this Q dot is constant. That means I can say the product of K and dt by dx is constant. So forget about the minus sign here. Na? Minus sign only shows in the direction of the heat transfer, the temperature decreases. So forget about the minus sign here, right? Now see, Q dot is not a function of x. That means I can say in x direction, the product of K and dt by dx is constant. Is it fine? So if K increases, the dt by dx decreases, right? If K increases, the dt by dx decreases, and vice versa. Is it fine? Is it fine? Now this is, you remember this concept? From here, you can easily comment on the temperature profile. Right? Now see, in x direction, see the wall, right? In x direction, see the x direction. Temperature increases or decreases? Sir, temperature decreases. In x direction, temperature increases or decreases? Temperature decreases. See, here the temperature is T1, here the temperature is T2. T1 is greater than T2, right? T1 is greater than T2. That's why the rate of conduction heat transfer in the positive x direction, na? T1 is greater than T2. So in x direction, the temperature decreases. In x direction, the temperature decreases. If temperature decreases, see, from this mathematical expression, if temperature decreases, because beta is positive, if temperature decreases, that means K decreases. If temperature decreases, that means K decreases, because beta is positive. So if K decreases, from this logic, it is very much clear that dt by dx increases. dt by dx increases. Right? So if beta is positive, K decreases, dt by dx increases. Right? Or if I say if beta is positive, then in positive x direction temperature decreases. If temperature decreases, K decreases, dt by dx increases. Now dt by dx increases. Now you can draw a temperature profile in such a way that dt by dx, that means slope of the temperature profile increases in the positive x direction. Is it fine? Right? So draw the temperature profile. So in case of the linear profile, everywhere that dt by dx is same, everywhere theta is same, everywhere dt by dx is same in case of the linear profile. Now draw the temperature profile in such a way that dt by dx, that means slope, increases in the positive x direction. So see, this is the temperature profile. This is the temperature profile, right? If you see slope here, if you see slope here, if you see slope here, and if you see slope here, right, you can easily comment the slope increases in the positive x direction. Now see, if you want to check the slope, draw the tangent to this point, draw the horizontal line, right? Similarly, if you want to check the slope here, draw tangent to this point and draw the horizontal line, right? Here slope is theta 1, here slope is theta 2, right? And it is very much clear that theta 2 is greater than the theta 1, that theta 2 is greater than the theta 1. Is it fine? So in case of the beta positive, in case of the positive beta, this is the temperature profile. This is the temperature profile. Is it fine? Is it clear? Now come to the case number 3. Come to the case number 3. Case number 3. Case number 3. Come to the case number 3. If beta is negative, so if beta is negative, then k is equal to k naught 1 minus beta t. K is equal to k naught 1 minus beta t. Fine. Now again I am considering this plane wall. Now this phase having temperature T1 and this phase having temperature T2, right? This is the x direction. This is the x direction. In x direction, again T1 greater than the T2, and in x direction temperature decreases. So this is the direction of conduction heat transfer. In x direction temperature decreases, right? Now see, beta is negative. Beta is negative. What is the meaning of that? If temperature decreases, then k increases, right? In x direction, see, in x direction temperature decreases now, temperature decreases, and minus sign is there. So if temperature increases, this whole term increases, right? And that's why that k increases. That's why k increases. And if k increases, then the product of k and dt by dx is constant. So if k increases, that dt by dx decreases. dt by dx decreases. So in this case, draw a temperature profile in such a way, in x direction the dt by dx decreases. In x direction the dt by dx decreases. Is it fine? Right. Now draw the temperature profile in such a way, in x direction that dt by dx decreases. That means slope decreases. Okay, see. Like this. Okay, so now you want to check that slope decreases or not. So if you want to check, take a 2 points, draw a tangent here. This is the horizontal line, this is the theta 1. Now draw a tangent here, draw a horizontal line, this is theta 2. So it is very much clear, theta 2 is lesser than the theta 1. So in x direction, this temperature profile having decreasing slope. Is it fine? So this is the temperature profile for the beta negative, right? So if you want to summarize all these 3 cases, if you want to summarize all three cases, so we can summarize here. See, okay. So this is the temperature T1. Here the temperature is T2, right? K is equal to K naught 1 plus beta T. K is equal to K naught 1 plus beta T, right? Now if beta is 0, then this is the temperature profile linear. This is the temperature profile. If beta is positive, then this is the temperature profile. This is the temperature profile. If beta is positive, if beta is 0, this is the temperature profile. And if beta is negative, this is the temperature profile. If beta is negative, right? So I hope you can understand this. Is it clear? Okay. Now next objective is, the first objective is find the temperature variation. The second objective is find the rate of conduction heat transfer. So if thermal conductivity is constant, then calculating the rate of conduction heat transfer, that is easy. We already calculated this part. Now if thermal conductivity is variable, if thermal conductivity varies, then how you can find out the rate of conduction heat transfer? Okay. So next heading is rate of conduction heat transfer. Find the rate of conduction heat transfer. Find the rate of conduction heat transfer. Right. So again, I am considering this plane wall only. I am considering this plane wall only. Okay. Now, here the temperature is T1. Here the temperature is T2. I am considering T1 is greater than T2. I am considering T1 is greater than T2. Fine. So the rate of conduction heat transfer occurs now. Rate of conduction heat transfer occurs. That is Q dot. Okay. What is the thickness of the wall? So thickness of the wall is delta. Thickness of the wall is delta. Thickness of the wall is delta. This is x direction. This is x direction. Is it fine? Now, to calculate the rate of conduction heat transfer, I am considering a very small element. Why I am considering a small element? Because the thermal conductivity varies now. In x direction, the thermal conductivity varies. If something is varying, right? If any parameter is variable, then take a small elemental area, right? Take a small elemental area, then find the let us assume in this case I am considering a small elemental area, then I am finding the small elemental heat transfer, then I am integrating it, then I will find the total heat transfer. So this is the way, right? If some parameter is variable, and if you want to total heat transfer, Thermal conductivity is variable, and I want to find out the total heat transfer. So there is an integration concept, right? So I'm considering a small elemental area or a small element. I'm considering a small element. So at a x distance, I'm considering this small element. This small element. Okay, and the thickness of this small element is dx, right? So I take out this small element. I will take out this small element, and I'm showing here. Okay, so this is a small element. Okay, now what is the thickness? The thickness is dx. The thickness is dx, and let us assume for this small element the temperature difference across the wall is dt. Here the temperature is T plus dt, and here the temperature is Tt, and the rate of heat transfer is dq dot. The rate of conduction heat transfer is dq dot for this small element, right? And what is the area which is normal to the direction of heat transfer? That is A only, na? Here also A, here also A. Is it fine? So from the Fourier law of heat conduction, for this small element, we can write that dq dot is equal to, this is minus Ka dt by dx. Yes or no? Yes or no? Yes, sir. From the Fourier law of heat conduction, that small elemental rate of conduction heat transfer, that dq dot is equal to minus Ka dt by dx, right? Now see, we already discussed the rate of conduction heat transfer in the x direction is not a function of x. Is not a function of x. Is not a function of x, right? From here, the conduction heat transfer is q dot. From here, the conduction heat transfer is q dot. From here, the conduction heat transfer is q dot. From here, the conduction heat transfer is q dot. From here, the conduction heat transfer is q dot. That means from the small element, the rate of conduction heat transfer is q dot only. So I can say this dq dot is equal to q dot only. Yes or no? This dq dot is equal to q dot only, because q dot is not a function of x, na? Q dot is not a function of x. If q dot is not a function of x, then if you take a small element, right? If you take the small element, then from the small element, the rate of conduction heat transfer is same as the q dot, na? So dq dot is equal to q dot. So simply we can write that q dot is equal to minus Ka dt by dx. Minus Ka dt by dx, right? So from here you can write q dot into dx is equal to, this is minus Ka and dt. Right. Now see, q dot into dx is equal to, that is minus Ka dt, right? So shall we integrate it? क्या हम इसको integrate कर सकते हैं? Shall we integrate it? Right? Yes. Integrate. So what is the limit? The limit is x is equal to 0 to x is equal to delta, and here the limit is, है ना, temperature limit. So at x is equal to 0, the temperature is T1, and at x is equal to delta, the temperature is T2, right? Put k is equal to k naught, 1 plus beta T, because I am assuming this variation for the thermal conductivity, na? K is equal to k naught 1 plus beta T, right? K is equal to k naught 1 plus beta T. If that variation of thermal conductivity with temperature is given, k is equal to k naught 1 plus alpha T plus beta T square, then put here, right? So whatever the variation of thermal conductivity is given, with temperature is given, put here, right? So now q dot q dot integration 0 tends to x, 0 tends to delta dx is equal to, a is constant, a is not changing with respect to x, right? Take it out, minus ka minus a, right? And this is k dt. K is a function of t, na? K is a function of t, and this is dt, right? Limit t1 to t2, right? Take a area, cross sectional area. So we, if you rearrange this, so q dot, this is the flux into, if you are integrating it, this is delta, that is equal to integration t1 to t2, and this is the k of t dt. So this is the general, this is the general mathematical expression. This is the general mathematical expression, right? Now, if thermal conductivity changing with respect to temperature linearly, then put here. So q dot into delta is equal to that is minus integration t1 to t2 k naught 1 plus beta t dt. Okay, so ultimately what you are getting ultimately after solving this, because q dot into delta is equal to minus k naught, and this is t plus beta t square, and this is t1 to t2, and this is minus k naught, right? t2 minus t1 plus beta t2 square minus t1 square, right? This is q dot into delta, and ultimately what you are getting, that q dot is equal to minus km, or I say this is km t1 minus t2, km t1 minus t2 divided by delta. After solving this, what you are getting this q dot is equal to km t1 minus t2 by delta, or you can say that q dot is equal to, that is km a t1 minus t2 by delta, right? And what is the km? This km is thermal conductivity at mean temperature. This km is thermal conductivity at mean temperature. Thermal conductivity at mean temperature. So what is the mean temperature? The mean temperature is Tm is equal to T1 plus T2 by 2, right? So Km is equal to, that is K naught 1 plus beta Tm, right? So Km is the thermal conductivity at the mean temperature. So I hope you can understand this concept. But remember, this mathematical expression, this expression is applicable only when the thermal conductivity linearly varies with temperature. This mathematical expression is applicable only when thermal conductivity K varies linearly with temperature. Right? K varies linearly with temperature, then only this mathematical expression is applicable. If K is not varying with temperature linearly, if it varies non-linearly, then then still there is no worry, right? Use this basic thing. Just whatever the variation of thermal conductivity with temperature is given, put here, simply integrate, you are getting the answer. Is it clear? So this is all about the variable. Okay, so next topic is effect of the variable area, right? So if area is changing with respect to x, if area is changing, then how we are calculating the rate of conduction heat transfer and the temperature variation, right? So next topic is effect of variable area, effect of variable effect of variable area, effect of variable area. Okay. So to understand this topic, I'm considering a non-prismatic member, or you can say non-prismatic rod. Non-prismatic rod. So this is the rod in which it is very much clear that area is changing. Okay. And the lateral surfaces, or you can say that outer surfaces are insulated. Outer surfaces are insulated. Right. So this length, I'm considering this length as L, this length as L, right? And at x is equal to 0, here the temperature is T1, and here the temperature is T2, right? This is the x is equal to 0, and this is x is equal to L. And I'm assuming that T1 is greater than T2. T1 is greater than T2, right? So if T1 is greater than T2, then definitely that conduction heat transfer occurs from this rod. Conduction heat transfer occurs from this rod, and let us assume this rate of conduction heat transfer is Q dot. So I want to find out two things here. One is the temperature variation, right? One is the temperature variation, how the temperature is changing with respect to x, how the temperature is changing with respect to it, how the temperature is changing with respect to x, right? And second thing, the rate of conduction heat transfer from this rod. Okay. So I'm considering some assumptions here, right? Without assumption, it is very complicated to analyze the things. So I'm considering some assumptions. So first assumption is one dimensional. First assumption is 1D. 1D. And here it is clear that direction is x direction. Okay. Now second assumption is no internal heat generation within this rod. No internal heat generation. No internal heat generation within this wall. Okay. Third assumption is steady state. Third assumption is steady state. Fourth assumption is thermal conductivity is not changing with respect to temperature. That means thermal conductivity is constant. Thermal conductivity is constant. Thermal conductivity is constant. Thermal conductivity is constant, right? And area is a function of x. Area is changing with respect to x, so area is function of x. Area is function of x, right? So I want to calculate the two things, right? One is temperature variation with respect to x, and second one is the rate of conduction heat transfer. To calculate this, I'm considering a small element at a distance x. So from the x is equal to 0, I'm considering a small element. So this is a small element. This is the small element. This is the small element. Right? This is the small element. And what is the thickness of this small element? So I'm considering the thickness of this small element is dx, and the temperature difference across this small element, that is dt. Area is ax. Area is ax, right? What is the area for this small element? That is the ax. Okay. And also I'm assuming that the rate of conduction heat transfer from this small element is dq dot. So if I ask you what is the relation between the q dot and the dq dot, so what is your answer? What is the relation between q dot and the dq dot? So what is your answer? Right, so the q dot and dq dot is same because q dot is not changing with respect to x. Right, the rate of conduction heat transfer is not a function of x. Rate of conduction heat transfer is not a function of x. Right, here the rate of conduction heat transfer q dot. Here the rate of conduction heat transfer, that is q dot. Here the rate of conduction heat transfer, that is a q dot. Here the rate of conduction heat transfer, that is a q dot. That means that q dot is not function of x. If q dot is not a function of x, then simply we can write that dq dot is equal to q dot only. That dq dot is equal to q dot only. Is it clear? Right. Now, use the Fourier law of heat conduction. Use the Fourier law of heat conduction. 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 So if you are using the Fourier law of heat conduction, so we can write that q dot is equal to, that is minus k, area is changing with respect to x, so a of x dt by dx, right? Now q dot into dx divided by a of x, right? And this is equal to minus k dt, right? So we can arrange the terms in this way, right? Now see, I want to calculate the total heat transfer. I want to calculate the total heat transfer, right? So total heat transfer we can calculate by integration, right? So q dot is constant, it is not a function of x, right? Dx a of x is equal to, I am assuming k is also constant, so minus k, that is dt, right? Now put the limit. What is the limit? X is equal to 0 to x is equal to L. And at x is equal to 0, the temperature is T1. And at x is equal to L, the temperature is T2. Right. So from here, we can calculate the q dot. Right. From here, we can calculate the q dot. So q dot integration 0 to L dx a of x is equal to minus k T2 minus T1. Right. So right now we are not, we don't know how the area is changing with respect to x. Right now we don't know how the area is changing with respect to x. But if we know the area, how the area is changing with respect to x, then we can easily calculate the q dot. So this is the concept. You remember the concept, then if you are getting the problem, then easily you are able to solve those problems, right? And if you want to find out the temperature variation with x, how the temperature is changing with respect to x, right? Because if there is a prismatic wall, then we already discussed that temperature is linearly changing with respect to x, right? If prismatic wall is there, if wall is like this, we already discussed, if wall is like this, and thermal conductivity is constant, then how the temperature changes with respect to x? How the temperature changes? The temperature changes linearly. But here the temperature variation is not linear. Why it is not linear? Right? Because area is not constant, area is variable. So to find the temperature variation, you should know the variation of area. You should know the variation of area, how the area changing with respect to x, right? So let us assume at a distance x, at x distance, at a distance x, at a distance x, the temperature is T, right? At a distance x here, the temperature is T. At a distance x, the temperature is T. Temperature is T. So how this temperature changing with respect to x, right? So at x is equal to, at a distance x, the temperature is T. So Q dot is equal to minus K A of x dt by dx, right? So this is Q dot into dx A of x is equal to minus K, and this is dt, right? Now integrate at x is equal to 0 to x, and at x is equal to 0, the temperature is T1, and at x is equal to x, the temperature is T. So from here, you can easily calculate how the temperature changing with respect to x. Right? From here, you can easily calculate how the temperature is changing with respect to x. Is it fine? So this is the effect of variable area. Effect of variable area. Okay. Now come to the next topic. And that topic is very, very important, and that topic is plane wall with internal heat generation, right? So far we are not considering the internal heat generation term. So far we are not considering that, but now we are considering, right? Now we are considering the internal heat generation term, right? So if there is a plane wall, in which that internal heat generation occurs, then how the temperature is changing, with respect to space, right? And how we are calculating the rate of heat transfer, rate of conduction heat transfer. So let's see, right? So next topic is plane wall with internal heat generation. 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 So this is next topic. Okay, now to understand this topic, I am considering a plane wall. To understand this topic, I am considering a plane wall. So this is the plane wall. This is a plane wall. Okay. And I am considering there is uniform internal heat generation. Sorry. Right. So this is a plane wall. And in this plane wall, I am considering uniform heat generation. That uniform heat generation, and that is Q dot G. So inside the plane wall, there is a heat generation, and that heat generation is uniform. Right. There are two ways. Through which that uniform heat generation, in this particular case, that uniform heat generation is there. But might be in future you are facing a problem where that heat generation is non-uniform, right? But right now we are discussing a problem where the heat generation is uniform, right? So that heat generation is uniform. So what is the Q dot G? So I said this Q dot G, we already discussed that heat generation is a volumetric phenomena. And that's why we are considering the volumetric heat generation rate. So Q dot G is uniform volumetric heat generation rate. Uniform volumetric heat generation rate. Right? That Q dot G is uniform volumetric heat generation rate, right? And what is the unit? That unit is watt per meter cube. Watt per meter cube. Okay. And apart from this, there are another assumptions also. And what are those assumptions? What are those assumptions? Right? That one dimensional, and in one dimensional the direction is x direction. Steady state, steady state, steady state heat generation is there, uniform volumetric heat generation is there. And next assumption is K is constant. Next assumption is K is constant. That means thermal conductivity. Thermal conductivity is not changing with respect to temperature, right? Next assumption is area is also constant. Area is not a function of x. Area is constant. Area is constant, right? So this is the x direction. And what is the thickness of this wall? The thickness of this wall is delta. Thickness of this wall is delta, and the cross sectional area is A. A is the cross sectional area, right? So internal heat generation is there, and this is the left face, this is the left face, this is the right face, and I am considering the left face temperature is T1 and the right face temperature is T2. Right face temperature is T2, right? Due to that internal heat generation, the left face temperature reaches to T1 and the right face temperature reaches to T2, right? So this is a general case, right? This is a general case, right? Might be T1 is equal to T2 also, T1 is equal to T2 also, right? But right now I'm discussing the general case, right? Then we will discuss the another cases like T1 is equal to T2, then what happened, like that. Okay, now see, again there are two objectives, right? In such type of problem, there are two objectives. The first objective is find the temperature variation with respect to x, how the temperature changes with respect to x, right? And the second objective is find the location where the temperature is maximum. Find the location where the temperature is maximum, and what is the maximum temperature, right? See, in this problem, that whatever the heat generation is there, that is equal to the conduction only, right? Whatever the heat generation occurs inside the slab or inside the plane wall, that is equal to conduction heat transfer only, that is equal to rate of conduction heat transfer only. So rate of conduction heat transfer, we know whatever the amount of heat energy is generated, that is equal to rate of conduction heat transfer from this wall, right? So here in such type of problem, basically two types of questions are asked. The first question is find the temperature variation, right? So here the temperature variation with respect to x, and second one is the find the location of maximum temperature and the maximum temperature. Okay, so to find out the answer of such questions, right, we will start from general heat conduction equation. We will start the analysis from the general heat conduction equation, right? So in Cartesian coordinate, we know the general heat conduction equation. In Cartesian coordinate, we know the general heat conduction equation, right? And what is the general heat conduction equation? That is del square T plus Q dot G by K is equal to 1 by alpha del T by del tau. 1 by alpha del T by del tau. Is it fine? Now see, steady state is, there is a steady state. That assumption is steady state. So if there is a steady state, so this term is 0, right? There is a one dimensional, and in one dimension, the direction is x direction. So instead of del square T, we can directly write d square T by dx square. D square T by dx square. Okay, so ultimately what you are getting this equation d square t by dx square plus q dot g by k is equal to 0, right? The temperature is only function of x. Temperature is only function of x. So how the temperature is changing with respect to x? This is the question. Okay. To solve, or if you want to answer of this question, how the temperature is changing with respect to x, solve this equation. Solve this equation, right? So if you are solving this equation, so this is d square t by dx square is equal to, this is minus q dot g by k, minus q dot g by k, right? Now integrate. So integrate once. So this is dt by dx is equal to minus q dot g by k, minus q dot g by k into x plus c1. c1 is the integration constant. Now integrate once again. So that is t is equal to minus q dot g by k x square by 2 plus c1x plus c2, where c1 and c2 are integration constant. c1 and c2 are integration constant. C1 and C2 are integration constant. So to calculate the C1 and C2, there are need of the boundary conditions. Okay. How many boundary conditions are required? So two boundary conditions are required, right? C1 and C2 are two integration constant. So two boundary conditions are required. Okay. And what are those boundary conditions? What are those boundary conditions? So we can say na, at x is equal to 0. See, this is x is equal to 0. And this is the x is equal to delta. So T1 is known, T2 is known. So what are the boundary conditions? The first boundary condition is at x is equal to 0, that T is equal to T1. And second boundary condition is at x is equal to delta, T is equal to T2. So these are the boundary conditions. Boundary conditions. Boundary conditions, right? Now use this boundary condition and find the value of C1 and C2. Right? Use this boundary condition and find the value of C1 and C2. So T is equal to minus Q dot G by 2K x square plus C1x plus C2. C1x plus C2. Right? So use two boundary condition and find the value of C1 and C2. Very simple, right? After finding value of C1 and C2, after finding the value of C1 and the C2, what you are getting, right? The final expression I am writing here, right? You easily calculate the C1 and C2, right? You easily calculate the C1 and C2, and after finding the value of C1 and C2, right? Put here, arrange the terms little bit, right? Then you are getting this end expression which I am writing here, right? So T is equal to, this is T1 plus T2 minus T1 into x by delta plus Q dot G by 2K delta x minus x square. Delta x minus x square. So this is the mathematical expression for the temperature. This is the mathematical expression for the temperature variation, right? This is very, very important. That T of x is equal to T1 plus T2 minus T1, T1 plus T2 minus T1 into x by delta plus Q dot G by 2K delta x minus x square, right? So from this mathematical expression, it is clear how the temperature is changing with respect to x, how the temperature changing with respect to x. So that temperature changes with respect to x is the second degree parabola, x square term is there, na? X square term is there. So how the temperature changing with respect to x? So that is second degree parabola. Second degree parabola. Is it fine? Right. So this is the temperature variation with respect to x. How the temperature changing with respect to x? That is second degree parabola. Right. So that is the first objective. First objective is find the variation of temperature. Right. The second objective is find the location of maximum temperature and the maximum temperature. So to get the location of maximum temperature, now see here, to get the location of maximum temperature, location of maximum temperature, to get the location of maximum temperature, dt by dx is equal to 0. Use the maximum minima concept, right? dt by dx is equal to 0 because x is the variable, है ना? So dt by dx is equal to 0 and dt by dx is equal to 0. So d by dx, what is the t? This is t1 plus t2 minus t1 into x by delta plus q dot g by 2k delta x minus x square, and this is equal to 0, right? So from here what you are getting, this t1 differentiation of t1 is 0, so this is t2 minus t1 into 1 by delta plus q dot g by 2k, and this is delta minus 2x. This is equal to 0. Find the x from here. So that is q dot g by 2k delta minus 2x, and this is equal to t1 minus t2 1 by delta. Okay, now see that delta minus 2x is equal to that is 2k by delta 2k by delta 2k by delta by q dot g and that is t1 minus t2 right? So 2x, or simply I say x is equal to that is delta by 2 minus that is k by q dot g into delta, and that is t1 minus t2. Now see 2x, so 2x on this side, delta minus 2k by delta into 1 by q dot g, t1 minus t2. Now take 2 in the denominator, so delta by 2. Okay, fine. So this is the location of the maximum temperature. X is equal to delta by 2 minus k upon q dot g by delta, k upon q dot g into delta t1 minus t2. Okay, so see here, there is no need to remember this mathematical expression now. Right? You remember this mathematical expression only. Right? And if in a question it is asked find the location of the maximum temperature, so simply differentiate it. And after differentiating equal to 0, right? So from that particular concept, you easily find the location of maximum temperature. So there is no need to remember this mathematical expression. इस mathematical expression को याद करने की need नहीं है. No need to remember this mathematical expression. Is it fine? Right? Now see here. Now I'm considering three cases here. I'm considering three cases here, right? That first case is if T1 is greater than T2, then if T1 is greater than T2. So if T1 is greater than T2, see here, if T1 is greater than T2, that means this term is positive now, this whole term is positive. If T1 is greater than T2, then this whole term is positive, right? That means delta, that location of the maximum temperature is, can I write in this way, that x is lesser than delta by 2. Okay, please try to understand. If T1 is greater than T2, then this whole term is positive, right? And delta by 2 minus something. So delta by 2 minus something, that is less than delta by 2 now. So if T1 is greater than T2, then location of maximum temperature, the location of maximum temperature is less than delta by 2, right? That means, see here, that means this is your wall in which uniform heat generation is there, right? The total thickness is delta by 2. Sorry, total thickness is delta, and this is the mid plane. This is the mid plane. This is the mid plane, right? So total thickness is delta. Total thickness is delta, and this is delta by 2, and this is delta by 2. Fine. So that location of maximum temperature is less than delta by 2. That means somewhere, okay, fine. Now here the temperature is T1, here the temperature is T1, and here the temperature is T2. Fine. And T1 is greater than T2. T1 is greater than T2. So if T1 is greater than T2, then see, the location of the maximum temperature is less than delta by 2 na? Location of maximum temperature is less than delta by 2. So delta by 2, that means let us assume somewhere here, somewhere here, somewhere here. Let us assume. Fine. So here the temperature is maximum. Here the temperature is maximum. Here the temperature is maximum, right? And what is the maximum temperature? What is the maximum temperature? You are calculating the x from here. You are calculating the location of maximum temperature from here. Okay? And once you know the location of maximum temperature, put the value of x here, right? You are getting the maximum temperature. You are getting the maximum temperature, right? Now see, the temperature variation. The temperature variation is second degree parabola. So here the temperature is maximum, here the temperature is T1. See, this is the temperature variation. Okay, this is the temperature variation. Here the temperature is maximum, here the temperature is T1, and here the temperature is T2. Right? So that conduction heat transfer occurs, from this side also. That conduction heat transfer occurs from this side also. So let us assume this is a Q dot 2, and the conduction heat transfer occurs from this side also. So this is a Q dot 1. Q dot 1. And we know that Q dot 1 plus Q dot 2, this is the total rate of conduction heat transfer. This is equal to Q dot G, this is the volumetric heat generation, multiplied by volume of this plane wall. And what is the volume of this plane wall? This is A multiplied by delta. A multiplied by delta. So Q dot 1 plus Q dot 2 is equal to Q dot G multiplied by A into delta. Is it fine? So this is the case number 1. This is the case number 1. Now come to the case number 2. If T1 is lesser than T2, or I can say if T2 is greater than T1, then if T2 is greater than T1, then so this is your wall, right? This is your wall. That thickness is delta. That thickness is delta. This thickness is delta, right? And this is the mid plane. This is the mid plane. Fine. That means here to here delta by 2 and here to here delta by 2. This is the x direction. This is the x direction. Here also this is x direction. This is x direction. Okay. Now, if T1 is lesser than T2 or T2 is greater than T1, so T1 is here and T2 is here, right? So if T2 is greater than T1, now see from this mathematical expression, if T2 is greater than T1 or T1 is lesser than T2, that means this term is negative now. This term is negative, this term is negative, this term is negative. If this term is negative, so negative, negative, positive, that means x is greater than delta by 2 now. In this case, that x is greater than delta by 2. X is greater than delta by 2. So that location of maximum temperature is greater than delta by 2. That means the location of maximum temperature is somewhere here na? Somewhere here. X is greater than delta by 2. So this is the location of maximum temperature, and the maximum temperature is, let us assume this is T max. This is a T max. Okay. So again, draw the temperature variation. Sorry. So this is the temperature variation. Second degree parabola. Okay. This is the temperature variation. Take a second degree parabola. This is the location of maximum temperature, right? So conduction heat transfers. Conduction heat transfer occur in this direction. In this direction, that is a q dot 1, and the conduction heat transfer occurs in this direction. Okay. So and q dot 1 plus q dot 2 is equal to q dot g multiplied by volume of the plane wall. Is it fine? Right. Now come to the case number 3. Come to the case number 3. So these two cases are unsymmetric cases. Okay? These two cases, this case is an unsymmetric case. This case is also unsymmetric case. Now I am discussing the symmetric case. Symmetric case. What is the meaning of the symmetric case? So see, case number 3. In case number 3, T1 is equal to T2 is equal to, I am assuming, let us assume that is TW. Wall temperature, TW, that means wall temperature. So T1 is equal to T2 is equal to TW, right? So in this case, it is very much clear. See here, if T1 is equal to T2, that means x is equal to delta by 2. At x is equal to delta by 2. X is equal to delta by 2. So that location of maximum temperature is at the mid plane only. Is at the mid plane only. In symmetric case. See. Okay. And this is the mid plane. This is the mid plane. Here the temperature is TW. Here the temperature is TW. TW. Here also the temperature is TW. And maximum temperature is at the mid plane, T max. And this is the variation. Right? Second degree parabola. Second degree parabola. This is the location of the maximum temperature. At x is equal to delta by 2. X direction. This is delta by 2. Total thickness is delta. total thickness is delta. Okay, so these three cases, ठीक है, two cases are symmetric cases and one case, sorry, two cases are unsymmetric case and one case is symmetric case. So this is a symmetric case and the earlier cases are the unsymmetric cases, right? So I hope you can understand this part, that plane wall with internal heat generation, that uniform heat generation, uniform heat generation. Okay, now come to the next case. In this case, the plane internal heat generation is there, but that one face of the wall is adiabatic. One face of the wall is adiabatic, right? So next case, I say this is a case number, okay, case number 3, and this is a case number 4, right? This is a case number 3 na? Now this is case number 4. Case number 4. So this is the plane wall and this face is adiabatic. X is equal to 0. Total thickness is delta. And this is the x direction. This is the x direction. And the uniform heat generation is there. Uniform heat generation is there, and that is Q dot G. The uniform volumetric heat generation, that is Q dot G. And this cross sectional area is A. And here the temperature is TW. Here the temperature is TW. Okay. Now in this case, find out the temperature variation with X. Find the temperature variation with X. How the temperature is changing with respect to X, right? Or in X direction, how the temperature changes, right? So to answer this question, again we will start from the general heat conduction equation, right? Again we will start from the general heat conduction equation. So if you are starting from the general heat conduction equation, so directly I write d square t by dx square. So assumptions are same, na? Assumptions are same. So if you consider all those assumptions, you can simply write d square t by dx square plus q dot g by k is equal to 0, right? And after solving this equation, t of x is equal to t1, sorry, t of x is equal to, just 1 minute, t of x is equal to this one minus q dot, this one minus q dot g by 2k x square minus q dot g by 2k x square plus c1x plus c2, right? So again c1 and c2 are the integration constant, right? And if I want to value of c1 and c2, so use the boundary condition. So what are the boundary condition here? So first boundary condition is, at x is equal to delta, can I write t is equal to tw? At x is equal to delta, can I write t is equal to tw? Yes sir. At x is equal to delta, that t is equal to tw. Fine. Now second boundary condition. At x is equal to 0, this face is the adiabatic, na? At x is equal to 0, the left face, this is the left face, this is the right face. So left face is the adiabatic, na? So at x is equal to 0, can I write the rate of conduction heat transfer is 0? Because adiabatic, na? At x is equal to 0 face, left face is adiabatic. So I simply say, na, at x is equal to 0, the rate of conduction heat transfer is 0. If rate of conduction heat transfer is 0, so I can say this is from the Fourier law of heat conduction minus Ka dt by dx is equal to 0. So K is not equal to 0, A is not equal to 0, therefore that dt by dx is 0. So I simply say at x is equal to 0, that dt by dx is equal to 0. Is it clear? Right. So uh, here if you are integrating once, you are getting dt by dx. That dt by dx is equal to this is minus q dot g by k minus q dot g by k x plus c1, right? Dt by dx. If you are differentiating once again, you are getting this, na? Dt by dx is equal to minus q dot g by k x plus c1 plus c1 plus c1, right? So use these two boundary condition. Use two boundary conditions. Use these two boundary conditions, right? At x is equal to 0, dt by dx is equal to 0. Now see here. At x is equal to 0, dt by dx is equal to 0. At x is equal to 0, the dt by dx is equal to 0, c1 is 0. C1 is 0, right? Use the second boundary condition at x is equal to delta. T is equal to TW. So this is TW plus Q dot G by 2K delta square. C1 is 0 plus C2. From that expression, you will find the C2. C1 is 0. C2 you are calculating from here. Put the C1 and C2. You are getting the temperature variation with respect to X. So temperature variation with respect to X. And that is equal to TW plus, right? After arranging the term, you are getting this mathematical expression. That T of x is equal to TW plus Q dot G by 2K, and this is delta x minus x square. Delta x minus x square. Right? T of x is equal to TW plus Q dot G by 2K delta x minus x square. I am directly writing now. You can easily calculate the C1 and C2. Easily calculate. Right? So T of x is equal to TW plus Q dot G by 2K delta x minus x square, right? So again, it is very much clear from this mathematical expression that temperature variation is second degree parabola. The temperature variation is second degree parabola, right? And if you want to find the location of the maximum temperature, so where is the location of maximum temperature? Where is the location of maximum temperature? Just 1 minute. No, so this is Q dot G by 2K delta square minus x square. Sorry, this is delta square minus x square. This is delta square minus x square. T of x is equal to TW plus Q dot G by 2K delta square minus x square, right? So second degree parabola. So where is the location of maximum temperature? So from this mathematical expression, it is very much clear. At x is equal to 0, the temperature is maximum. At x is equal to 0, that temperature is maximum. And what is the maximum temperature? That maximum temperature is TW plus Q dot G by 2K delta square. This is the maximum temperature. This is the maximum temperature, right? T maximum is equal to TW plus Q dot G by 2K delta square. And where is the location of maximum temperature? The location of the maximum temperature is at x is equal to 0. Here the temperature is max, right? Temperature is maximum and dt by dx is equal to 0, right? Now here the temperature is TW. Here the temperature maximum, here the temperature is TW. Temperature variation is second degree parabola. This is the variation, second degree parabola. Is it clear? Second degree parabola. Second degree parabola. Okay, so I hope you can understand this concept, right? Now one thing, you can find out the maximum temperature in this case also. You can find out the maximum temperature in this case also. Yes, sir, we can find. Right? At x is equal to delta by 2, the T is equal to T max now. Right? And T of x is equal to T1 plus T2 minus T1 into x by delta plus Q dot G by 2K delta x minus x square. Right? Now at x is equal to at x is equal to delta by 2, the temperature is maximum. Now see, symmetric case is, this is symmetric case now. So T1 is equal to T2 is equal to TW. So this term is vanish. This is 0. So ultimately what you are getting, at x is equal to delta by 2, temperature is maximum. So T max is equal to T1 is equal to TW plus Q dot G by 2K, Q dot G by 2K, and this is delta x delta by 2 minus delta square by 4, right? Now T max is equal to TW plus, and this is Q dot G by, right, 4 is the LCM, so this is 2 4, okay, so this is 8K delta square. This is the maximum temperature. So in symmetric case, that maximum temperature is TW plus Q dot G by 8K delta square, right? This is the maximum temperature, right? And in unsymmetric cases, there is no need to remember any mathematical expression, right? There is no need to remember any mathematical expression. There is only one mathematical expression which is required to remember, and that is the temperature variation with respect to x. Differentiate with respect to x, equate with 0, and finally you are getting the location where the temperature is maximum. Put the value of x in the temperature variation expression, and from there you are getting the maximum temperature. Okay, so at least for this case, at least for the symmetric case, you remember this mathematical expression, and for case number 4 you remember this mathematical expression, Okay, so this is all about the plane wall with internal heat generation, Okay.